We're going to start off with Andy Moore talking to us about the origin of exceptional type 2A and 2B diamonds.
Okay, great. Thanks for the invite to give this talk, which I'm doing on behalf of myself and Herb. It's a project we've been working on for some time. And just to kick off some background, which most of which was covered by Farnes in his talk yesterday, but diamonds, of course, the high pressure form of carbon, and most diamonds have nitrogen as trace impurities, and these nitrogen bearing diamonds are called type 1 diamonds. There are a variety of different subgroups, but those aren't important to us at the moment. But nitrogen absorbs the blue wavelength, and so these diamonds, nitrogen bearing diamonds, often have a yellow color. Now, the inclusions in diamonds link them to the two main rock types of the upper mantle, peridotites down here in the bottom right, eclogites in the top right. And so the majority of diamonds seem to have been formed in association with these two rock types. On the left is the carbon isotopic signatures of these two groups, eclogites up here and here peridotites. This just shows the proportion of carbon 12 to carbon 13, with the light isotope carbon 12 increasing to the left. And both eclogitic and peridotic diamonds have a prominent isotopic peak at around -5, which is considered to represent the carbon isotopic signature of the upper mantle. And the eclogitic suite has a tail towards light carbon isotopic signatures. Now, these two graphs show what happens with compositions of, on the left, peridotic, on the right, eclogitic or basaltic composition with increasing depth in the mantle. So, for example, with increasing depth, olivine will revert to wadleyite and then to ringwoodite. And in addition to the dominant eclogitic and peridotic diamonds, there's a small population that have inclusions which indicate derivation from depths up to and possibly exceeding 600 kilometers. And these are termed super deep or sublithospheric diamonds, so third diamond paragenesis. Now, while the majority of diamonds have nitrogen impurities, there's a small population which lacks nitrogen. These are type 2 diamonds, so the name simply means nitrogen below detection limit. And as a result, these diamonds have a beautiful white color, and these are the exceptional type 2 diamonds. Can be very large. These are all from Lesotho. This is the Lesotho Promise, which weighed in at 603 carats. So these are the diamonds we will be talking about today. Then there's a subpopulation of the nitrogen-free suite that has boron as an impurity. And when boron's present, this gives the diamonds a blue color. And these are the type 2B diamonds. Now, the majority of the largest gemstones are all exceptional type 2s, or certainly the majority. These are the three largest. At the top, the famous Cullinan stone, which weighed in at over 3,000 carats or over 600 grams. And something that probably strikes everyone about these stones is that they don't have the nice crystal shapes which Farnes discussed in his talk yesterday. They're all irregular. And this is a characteristic of these stones. One of the other characteristics is that they often have graphite as an inclusion, but other inclusions which might link them to one or other mantle paragenesis are rare. And because of this, the origin of these diamonds has long been enigmatic, and one of the important reasons is that inclusions are very rare in these stones. Now, in a study by Evan Smith and co-workers published in Science in 2016, They coined the acronym CLIPPER for these exceptional type 2 stones, which stands for Cullinan-like, large, inclusion poor, relatively pure, in other words, nitrogen below detection limit, irregularly shaped and resorbed. And I've highlighted irregularly shaped because you can generally simply recognize one of these clipper diamonds on the basis of its irregular shape with a high degree of confidence. So the irregular shape, one of the very characteristic features of these diamonds. They're highly important economically because they can have a big impact on kimberlite economics. So the presence of these stones in Litseng gives the diamond parcel an average value of when I last heard, $3,000 a carat. And this makes Litseng one of the lowest, in fact, the lowest grade diamond or kimberlite producer in the world. So it's obviously important to find out if these stones are present. And at the moment, the only way of doing this is to get a bulk sample, which is expensive. So it would be ideal to develop some sort of a proxy for predicting whether they are present or absent. And this requires an understanding of their formation. And there are two main models. The first, which is probably the most widely accepted, is that they have a super deep origin. And this is a model developed by Evan Smith and his co-workers. And if this model is correct, then developing a proxy, a predictive proxy, means that we have to understand low mantle processes and mineralogy. The second model, which I've been pushing for several years, is that they're part of the megacrystal suite. In other words, have a lithospheric origin. And if this model is appropriate, it means we've got to understand the origin and mineralogy of the megacrysts. So let's kick off by looking at the evidence for a sublithospheric origin. And this was based on screening of diamonds at the Gemological Institute of America by Evan and his co-workers, looking for type 2 stones with inclusions that differed from those in the known lithospheric and sublithospheric parageneses. In other words, different from those of the eclogitic, peridiotic, and known super deep diamonds. And they found diamonds which had sublithospheric, these are all nitrogen-free, obviously, and they found nitrogen-free stones with inclusions which indicated a sublithospheric provenance. It was a very, very meticulous study, and on the basis of this, they inferred that the Cullinan diamonds were, the clipper diamonds had a sublithospheric provenance. And it should be mentioned that one of the things they picked up was that the graphite inclusions, which are very common in type 2 diamonds, often were masking inclusions which hadn't previously been recognized. So a very careful study. And on the basis of these sublithospheric inclusions in these nitrogen-free diamonds, they inferred a sublithospheric origin for the clippers. A lot of the inclusions were nickel-iron alloys. But one of our concerns is if you look at these diamonds, a majority of the stones studied are quite inclusion-rich. And this conflicts with the definition of clippers, which are inclusion poor. So the abundance of inclusions raises a potential red flag for this model and possibly queries whether these diamonds are in fact linked, that they type 2 stones, certainly, but whether they link to the clipper suite. And this problem is illustrated at Cullinan, where you've sampled sublithospheric, peridiotic, and eclogitic diamonds, so a wide section of the mantle, and these diamonds at the bottom are the clippers from Cullinan. It's an important clipper producer. They have light carbon isotopic signatures biased towards carbon-12. And in these associations that you also find there, each of these associations has the black symbols are nitrogen-free diamonds. So in each of these three associations, they're nitrogen-free and by definition clipper diamonds. So this means that if you take this population, for instance, quite a large number of sublithospheric inclusions, is it related to the clipper population? These three parageneses are all biased towards isotopically heavier signatures, and this suggests that there isn't a link between, for instance, these stones and this population. So if you find a nitrogen-free stone with inclusions, you have to have reason to link it to the clipper population. Simply having a nitrogen-free stone on its own is not necessarily going to be a clipper stone. And this is further underlined at Letseng. These are the clipper stones, another important clipper producer, again biased towards light carbon isotopic signatures. And these are the sublithospheric stones. The black ones are the samples studied by Evan Smith and co-workers. They have heavier isotopic signatures, don't provide strong support for a link to this population. Doesn't rule it out. It's a very small population, but it certainly isn't shouting out that these sublithospheric diamonds are linked to the associated clipper suite. Then on the left-hand column is a list of the phases reported in the study, and a majority of these phases are present in alluvial diamonds at Juina, which contain a high proportion of sublithospheric stones. And the Juina alluvial deposit, this is in Brazil, is notable for having hydrogen as an impurity. This is actually rare in diamonds, and Kaminsky and Wirth said that the presence of hydrogen set the Juina stones, sublithospheric stones, apart from other diamond deposits worldwide, and hydrogen was reported from some of the diamonds in the study. So I believe this raises the query, is this a new paragenesis that differs from the known sublithospheric parageneses? I think this is debatable. Then a further problem with, not simply with their study, but just with inferring a sublithospheric provenance, is that CiSO3 has three polymorphs. The low pressure one is wollastonite. There's a high pressure one with a perovskite structure. This is rare. It's been reported in 1 and possibly 2 diamonds, but there are a number of diamonds that have the intermediate pressure polymorph. The blue area shows the stability field. It's named Brayite in honor of Gerhard Bray, the kimberlite experimental petrologist. And a number of occurrences of Brayite inclusions have been found. And when they've been present, it's been assumed that they have inverted from the high pressure form. But a number of workers have pointed out that this is problematic because Brayite can also crystallize under sublithospheric pressures in the appropriate compositions. So carbonate-rich and calcium-rich composition will crystallize Brayite at lithospheric conditions, in other words, down to about 7 gigapascals. So that raises the question, if you have a Brayite inclusion, what does it mean? And for example, this is a nitrogen-free stone. These are black graphite inclusions, probably. It's from the Williamson mine. The pink color, as Farnes mentioned yesterday, is the result of plastic deformation. And the morphology is shouting out that this is a clipper stone. It's a fairly large stone. So I don't think much debate about that. But what do the Brayout inclusions tell us? It was inferred to be in evidence for a sublithospheric provenance, but I think it's completely compatible with the lithospheric provenance. So in other words, the presence of Brayout inclusions isn't conclusive. So these are some of the concerns that we have about the sublithospheric model. Firstly, many of the samples were inclusion rich. It infers a hitherto unrecognized paragenesis, but most of the phases also occur in the sublithospheric population at Juína in Brazil. Is the problem in interpretation of Brayout. And then at Litseng, although there's only a small number of sublithospheric diamonds, they don't shout out for a link to the associated clippers at this important clipper locality. And we believe that collectively, this evidence argues against a sublithospheric origin for the clipper type 2 diamonds. So let's look at the evidence for clipper megacrystal link. This is one of the classic photographs from the Lesotho kimberlite volume of a group of megacrysts. This is a centimeter scale, and the definition of a megacryst by Ben Hart is that they monomineralic nodules greater than 10 millimeters in diameter. The common phases are garnet, illustrated here, olivine, orthopyroxene, clinopyroxene, and ilmenite, and also a number of other rare phases, but including zircons. Now, in addition to these large nodules, you get much rarer inclusions in kimberlite. This is a pyroxene ilmenite intergrowth, and the composition of the phases is very similar to those of the megacryst suite. So this suggests a link to the megacryst suite. That's a large section, and this is a detail of this area in here. And this shows a texture called comb layering, which indicates rapid crystallization or quenching. So the compositions of the minerals link this to the megacryst suite, but the texture indicates that this crystallized rapidly. Then the megacrysts have been divided into two populations, which are often regarded as separate populations. These are the clinopyroxenes, the garnets, and the orthopyroxenes, olivine down here. And the red population is chrome-rich, and the orange population chrome-poor. So the megacrysts are divided into chrome-rich and chrome-poor subpopulations, although these seem to be present in the majority of kimberlites. And very occasionally, you seem to see these two associations in the same hand specimen. The gray represents an orthopyroxene megacryst, and this hosts an orange garnet, which matches low chrome megacryst composition, and in turn encloses a garnet with compositions very similar to the chrome-rich suite. So very occasionally you see these two populations in the same hand specimen. So just to summarize some of the, or emphasize some of the most important characteristics, firstly, large size, a subset with textures indicating rapid crystallization, chrome-rich and chrome-poor subsuites, which very occasionally coexist in the same hand specimen. Zircon is a minor member of the megacryst suites. Where these have been dated, they give ages that are very similar to the host kimberlite. So this indicates crystallization. just prior to incorporation. So this suggests that the megacrust suite had a very short mantle residence time. And you sometimes see carbonate inclusions, and this is pointing to a carbonate-rich parental magma. Now, before we talk about the clipper diamonds, the exceptional type 2 diamonds, we're going to have a diversion and just discuss some of the characteristics of an enigmatic group of diamonds called phragmicites. They're polycrystalline, composed of tiny little crystallites. The origin is considered highly enigmatic. This is another specimen, and this is a somewhat coarser specimen over here. So polycrystalline diamonds, phragmicites, and what do they tell us about diamonds in general? Now, these are some of the most important characteristics. They can be quite large. They're polycrystalline, interpreted to reflect rapid crystallization. They have inclusions which have been classified as websteritic, but there's a problem with websteritic compositions because they show a strong overlap with those of the megacrust suite. So it's long been a problematic to distinguish between the websterites and the megacrusts. These, we'll talk about that shortly. These inclusions have been divided into chrome-rich and chrome-poor subsuites, but occasionally you see them in the same diamond. And occasionally these inclusions are zoned, and this is interpreted to reflect a short mantle residence time. Zoning wouldn't last long under mantle conditions, so crystallization shortly prior to kimberlite eruption. And some of them have carbonate inclusions. Then extremely important is that they have a very unusual and very diagnostic carbon isotopic signature, which is shown here. The bottom 4 panes for individual localities. The top is a composite. The red are phragmicites with inclusions, and the lighter color inclusion-free phragmicites. And at each of these localities where you've got a significant sample size, the majority are characterized by light carbon isotopic signatures with a peak somewhere around -18 to 20. But in each of these, there's a subpopulation with heavier isotopic signatures. So this overall signature of a light carbon isotopic rich composition associated with diamonds with or phragmicites with a heavier carbon isotopic signatures is a very characteristic, unusual overall characteristic, and very different from that of the eclogitic and the periditic suites. In terms of composition, this blue line shows the range of compositions of garnet inclusions from a group of samples from the Vienna Museum in Austria. The provenance of these phragmicites isn't certain, but it's believed to be Southern Africa and probably Botswana. And it's characterized by a range in MGFE, but relatively invariant low calcium contents. And this is typical of websterites. So on this basis, these have been classified as websteritic. The crosses are inclusions in Venetia diamonds, very similar low calcium with a range in MGFE. This includes some phragmicites. So these have also been classified as websteritic. The orange symbols, however, are megacrust compositions, and you can see there's a strong overlap. So this raises the question of whether these are linked to the megacrusts or the websterite suite. So compositions alone are not definitive, So we need to look at some other characteristics. And here I've compared the megacrysts to the phramosite. Both can be large by definition. There's a subgroup of megacrysts showing rapid crystallization textures. Phramosites show rapid crystallization textures. Both are broadly coeval or formed shortly before kimberlite eruption. Both have chrome-rich and chrome-poor subsuites, which may coexist in the same hand specimen or the same diamond. Both have carbonate inclusions and another number of other similarities. And we feel that these parallels are so dramatic, in addition to the compositional similarity of the phramosite inclusions to the megacryst suite, that this links the phramosites to the megacrysts. In other words, this is part of the megacryst suite. And this has a very important corollary, we believe, or we submit, that the megacryst suite must now be acknowledged as a distinct diamond paragenesis. That's in addition to the eclogitic, peridotitic, and sublithospheric, which includes phramosite diamonds, and that these are characterized by a highly distinctive carbon isotopic signature, which is shown again down here, eclogitic and peridotic signature on the right. And if you compare that to the clippers from Cullinan and Letseng, two important clipper producers, they're remarkable parallels. The majority at Letseng and Cullinan have light carbon isotopic signatures, but in both there's a subpopulation with heavier isotopic signatures. And just to compare them, these are the sublithospheric diamonds from Letseng. And we believe that, or we submit that there's such a similarity between the unusual signatures of the phramosites and the clippers at these two important localities, that this is arguing for a link between the clippers and the phramosites, with the implication if the phramosites are megacrysts, so are the clippers. And just to underline this textural characteristic of the megacrysts, as they're large, greater than 10 millimeters. This also applies to the exceptional diamond, type 2 diamonds, the clipper diamonds. And I don't think this is a trivial petrographic observation. I think it's significant. So this raises the question of how the megacrysts form. And this is a further rather controversial signature. It's a controversial issue. But at Monastery, John Gurney and co-workers showed that the megacryst suite formed isobarically, but over a wide temperature range extending towards the diamond stability field. This is the graphite diamond inversion curve. The high temperature megacrysts were olivine, orthopyroxene, clinopyroxene, garnet, and the low temperature ones, ilmenite and zircons. So a range of isobaric crystallization over a range of temperatures. One of John Gurney's students, Jenny Hops, showed at Zhuaning you had a similar characteristic, isobaric crystallization over a range of temperatures extending into the diamond stability field. And Ben Hart and John Gurney proposed a model along these lines to account for this isobaric crystallization over a range of temperatures. And this is my attempt to represent it. So this is my artwork, but I'll try and give an outline of their model. That they envisaged a pooled magma body in the mantle, surrounded by a thermal aureole, they were silent on the nature of the magma, but I believe it's the kimberlite magma, but this isn't critical for the model. And they suggested that small volumes of this magma were injected into fractures in the surrounding thermal aureole, and these crystallized as pegmatitic veins. So the megacrysts are parts of pegmatitic veins crystallizing down this thermal gradient. And we suggest that the megacrysts, the type 2 diamonds, the clippers, are part of the megacryst suite, and they formed at the low temperature end of this range. So something like this. As you get into low temperatures, you potentially cross into the diamond stability field, and diamond can crystallize. Presumably, the mantle rocks must have buffered these megacryst magmas to low FO2, which is also important for crystallization. So we propose that these exceptional type 2s are low temperature members of the megacryst suite, and at these low temperatures, you'd have had olivine and orthopyroxene and garnet fractionation. So these would probably be carbonate-rich and calcium-rich residual liquids. So these are just the compositions that could potentially crystallize brayite as a stable phase. And this could account for brayite in some of the exceptional clippers, as in that pink stone from Williamson. Now, what we further propose is, at the time of crystallization, you'd have probably got to heralding crystallization, fracturing of the mantle surrounding this magma body, and this would result in volatile loss from these residual magmas. Oh, sorry, I didn't point out, Dan Schulze has pointed out that the megacryst suite, the low temperature megacrysts, would be above the solidus, and he's noted that there would have been residual liquids. Sorry, I should have pointed that out. So these residual liquids left following megacryst fractionation, and we suggest that fracturing of the mantle prior to eruption would result in volatile loss, and if a magma loses volatile loss, this can trigger rapid crystallization. So we propose that this explains the formation of these nodules with quenched textures, and also the formation of the phragmocytes. So phragmocytes and the exceptional clippers, part of the megacryst suite. So let's just look at how this potentially tells us something about possible proxies for predicting these clippers. Now, the triangles are group 2 kimberlites, and none of the group 2 kimberlites is an important clipper producer. The clipper producers, or the important ones, are all group 1 kimberlites, Arapa and Jwaneng in Botswana, Jwaneng and Premier in South Africa, Letseng in Lesotho. So all of the important clipper producers are group 1 kimberlites. And so the first question is, why is it that you don't see clippers in the group 2 kimberlites? And this is a model that I suggested some time back. This is looking at the megacrysts in monastery. This is the study of John Gurney and co-workers. And they showed that the olivine megacrysts showed, with increasing iron content, showed progressively increasing titanium. And then these garnets were joined by ilmenite, and these are ilmenite garnet intergrowths often, and this resulted in a decrease in titanium. I don't know if you can see the bottom line, but this would be decreasing magnesium over here, and decreasing magnesium is broadly a proxy for decreasing temperature. So you'd have got crystallization of the monastery, the group 1 garnets over a relatively wide temperature range. These are garnet megacrysts from Star, which is a group 2 kimberlite. They show a much more restricted range, which don't get down to the same iron-rich composition. So we suggest this is indicating for some other reason not understood, but crystallization didn't extend over the same temperature range. So we suggest that in the group 2 kimberlites, relatively extensive megacrystallization takes you into the diamond stability field, but in the group 2 kimberlites, much less evolution of the megacryst suite for reasons not understood, but that's what the chemistry is saying, and the crystallization ends up in the graphite stability field, and as a result, the clippers don't form. So potential link between megacryst compositions and the absence of clippers. And this is further illustrated by olivine megacrysts, because not only are clippers rare in the group 2 kimberlites, but rare or absent, but they're very rare in the lac de Gras kimberlites in Canada. Now, if you look, we're now doing a quick diversion into olivines. This shows olivines from the Kimberley pipes, and the important feature are these gray symbols. These are olivine rims, and this would be a composite of all the Kimberley kimberlites. And relative to the composition of the rims, you get a group of iron-rich olivines. This is from a paper by Roger Mitchell and co-workers, and they've suggested that these are megacryst olivines, which is something that I'd suggested previously as well. So these iron-rich olivines relative to the rims are regarded as the chrome-rich megacryst population. This illustrates this for Letseng, an important clipper producer. These are the olivine edges, the crosses, and these are the relatively more iron-rich olivines, and they show reverse zonation. And the cores of these olivines go down to relatively iron-rich compositions, round about magnesium number of 81. Now, if you look at lac de Gras, the crosses again are the olivine margins. These are the relatively iron-rich olivines, and they show a relatively small range in MGFE, as far only as magnesium number of around 90. Finch and Newlands are group 2 kimberlites. Again, these are the edges, the crosses, and the iron-rich olivines again never get down to iron-rich. The iron-rich compositions that we see at Letseng, for example, they only get down to just about FO84, or magnesium number of 84. And so again, we get back to the same diagram. At Letseng, a wide range to iron-rich compositions suggests a wide temperature range of crystallization of the megacryst olivines, potentially going into the diamond stability field. But at places like Leslie was one of the kimberlites of the joining of the lac de Gras field, much less evolution, and you don't get out of the graphite stability field. So this is starting to look as though we might be on our way to getting a proxy to predict the presence or absence of clipper diamonds. But this illustrates one of the problems. The diamonds here are megacrysts these are actual megacrysts from monastery. They go down to very iron-rich compositions. That's great because clippers have been reported from monastery. So in monastery, the association seems to work. The triangles, though, are olivines from the Colossus kimberlite on the Zimbabwe craton. They also go down to fairly iron-rich compositions. but to my knowledge, clippers haven't been produced from Colossus. The diamonds that it's been mined and the diamonds recovered have all been small. So at Colossus, for whatever reason, maybe a different craton, the link between the iron-rich compositions isn't giving us evidence for the presence of clippers. So I think this is where we are at the moment, that megacrysts can help explain the absence of clippers. I suppose it's a bit of a step forward. It's not foolproof in predicting the presence of clipper diamonds. I don't think we've cracked this. It's still work in progress. And I believe that the key is going to be to refine our understanding of the origin of the megacryst suite. But an important corollary is that if there's a link between the range in megacryst compositions and the absence of clippers, I think this is strong additional evidence for a link between the clippers and the megacryst suite. Some intriguing evidence for the possible age of clipper diamonds, going back to this diagram where we pointed out that in each of the three mantle associations at Cullinan, the old formerly known as Premier mine, you get nitrogen-free diamonds, those are the black symbols, and then there's a spectrum of compositions into nitrogen-free diamonds. So in each of these, there's a compositional continuum from the nitrogen-free stones here as well into nitrogen-bearing compositions. So there's not a single box for group 2 kimberlites, type 2 diamonds, but in each association there's this compositional spectrum from nitrogen-free to nitrogen-bearing. And the diamond on the left is a nitrogen-bearing diamond. It's that's obvious from the yellow color, but this intense yellow-orange color is typical of a small subgroup of type 1 diamonds called type 1b diamonds. And these are characterized by the presence of single nitrogen atoms. So the nitrogen impurities are scattered through the carbon lattice. This is a fairly big stone. It would be nearly 14 carats, 14 millimeters across. And these 1B diamonds don't last long in the mantle, because what happens is very rapidly, certainly over less than 1 million years, the diamonds start, the nitrogen starts reorganizing itself into pairs of atoms. So this transition from the 1B to the paired nitrogen atoms takes place in less than 1 million years. So when you find these rare type 1B diamonds, they're young diamonds. They formed shortly before being caught up by the kimberlite. And one of the features that I think should strike you about this is they don't have nice crystal form. They're highly irregular, and in texture they look remarkably similar to the exceptional type 2 suite, the clipper suite. Another one here. This is the Cullinan diamond again, and we pointed out that this irregular morphology is such a characteristic feature of the clipper diamonds. You can actually recognize them on the basis of their morphology. And we suggest that the clippers and these 1B diamonds are part of the same paragenesis, the nitrogen-free extreme and a nitrogen-bearing extreme. So the implication is if these yellow 1B diamonds are young, the clippers are also young, and of course that's perfectly compatible with the megacryst model. And I think you've probably heard enough of my voice, so we'll sign out there. Thanks very much.
Thank you very much, Andy. That was a fascinating look at some really beautiful diamonds. We have plenty of time for questions. So if you'd just like to raise your hand, put a question in the chat, or even just ask your question.
Andy, just a question from me on whether or not you believe the diamonds, the type 2 diamonds with inclusions, you're saying they're not part of the clipper suite, but do you think they still come from super deep regions of the mantle?
Yeah, sure, Craig. I'm not. I don't think there's any doubt that some of the stones that Evan and co looked at were sublithospheric. There's no question about that. I mean, that was an important study, and you know, some of their stones were 10 carats, and it raises very, very important questions. I mean, how do you get a 10-carat stone to the surface? And of course, it was telling us a lot about the deep mantle. So you know, very important study. But we would argue simply that the stones that they studied, the majority of them were sublithospheric indeed, but not clippers.
And Ian, what age data do we actually have, so to speak, for these big stones, if any, or reliable data?
Well, the only I don't think we have any data, John, and the only evidence that I know is this evidence that I've discussed, that the morphology just is so striking. I've seen not a big cross section, but other type 1B stones that they produced quite a few of them in that Nauja pipe in, I think that's how you pronounce it, in Canada. And all of those were regular stones, highly unusual morphology. And if that was white, you'd have said it without any hesitation, it's a clipper. So that's the only evidence I can give, is the morphology links this to the clippers. These are young, there's no question about that. I don't think that's debated. And so I think, if, you know, the fact that every one of the parageneses shows a range from nitrogen-free to nitrogen-bearing, I don't think the clippers need to be different from that. And they've actually shown that there is a range, you know, there's some debate as to what you should call a clipper diamond. Should it be the detection limit, which used to be 20 ppm? Should it be 5 ppm? So we know that there's a range from at least 5 to 20 ppm, and probably more than that if you analyzed enough stones. But Farnes pointed out that the producers are very stingy about giving us stones to analyze.
Andy, there's a question from Mike Lynn on the chat. You just repeat the characteristics of the diamonds categorized as definitely sublithospheric?
That was based on the inclusions. For instance, there's majorite garnet, and that certainly is indicating a deep origin. And then there was some brayite. Now brayite, some of it may be inverted, the inverted perovskite structured form, the high pressure form. So we're not disputing that some of them might be inverted perovskite structured CaSO3, but the problem is that CaSO3 can also crystallize in the lithosphere. So basically, some of the inclusions are certainly sublithospheric.
I mean, the other thing that works quite well, obviously, Andy, is the light carbon isotopes. I mean, that feature also seems quite consistent.
These are the signatures, isotopic signatures of sublithospheric suites. And you can see that, I mean, some of them go down to light isotopic signatures. A lot of them have, at individual localities, are heavier. But none of them, for instance, the Jarvis-Fontaine suite overlaps the light part of the population at Letseng and Cullinan, but it lacks the heavier population. So you know, you don't get the striking. These ones are perhaps more similar, but the peaks up at what's this, -24. So collectively, the sublithospheric population does cover a wide range, but at individual localities, these look very different. Whereas with the Framercites, you know, there's such a parallel between the Framercite diamonds and the clippers. And then, of course, there's the, you know, one of the reasons for light isotopes is that you've got subducted material. But Cartinier has for a long time argued that, and I don't think the two models are exclusive, that if you have fractionation of a magma in the mantle, you'll lose CO2, which will take off the heavier isotope, and that the diamonds will progressively become lighter. So not many people seem to like this model, but you know, what you're saying is that the light isotopic signature is compatible with subduction, but there are other potential models that can also give you light isotopic signatures. And the megacrysts, of course, are lithospheric. They're not deep.
We've got another question in the chat box from Sean Johnson. What are your thoughts on the newly discovered davamayoite mineral? I hope I pronounced that one too badly. For classification of clippers. Why don't we see more of this mantle mineral in deep mantle derived diamonds?
Yeah, that is the only verified example of the uninverted form of CAPV. So it doesn't seem to, the argument is it doesn't seem to survive, it inverts. And so some of the brayite inclusions may be the inverted form of CaSiO3, and are generally assumed to represent inverted davamayoite. But the problem is, are all brayite inclusions inverted from the perovskite structured form? We argue that they can actually, not only we, a number of others have pointed out that that the brayite can crystallize under lithospheric conditions.
Yeah, I think it does, Andy. I mean, I think one of the things, and Farnes alluded to that, and we've talked about it, you know, you need more information, research on big diamonds or inclusions if they exist from big diamonds. I guess, unfortunately, for understandable reasons, you know, so much work has been done on, you know, generally small diamonds, and mostly it was done before we really appreciated the importance of the big clippers.
But just getting back to brayite, you know, if you have a kimberlitic magma or any magma and you take out olivine, orthopyroxene, and clinopyroxene, you're going to end up with, and the evidence is quite clear that the megacrysts were formed, they have carbonate inclusion, so indicates a carbonate-rich parental magma. And so you crystallize these magnesium-rich phases, and the end magma is going to be calcium and carbonate-rich. And, you know, the experimental evidence says this can crystallize brayite as a primary phase. And I suspect, I don't know what brayite looks like, but it may be, simply you're looking at large diamonds. We may just not be seeing them that often. I presume brayite is transparent. So we might find that, with more samples, that brayite is not as unusual as it, or as rare as we thought.
Good morning to the North Americans and Canadians. Hi to everyone else on our side. Just a short insight, and thanks to Andy and Farnes. Brilliant presentations, especially on what are type 2s and type 1A, Bs and things like that.
Okay, Tanya's going to move you, is that right, Tanya?
Yeah, that's good. Okay, so when I was at Letseng in 2006, Letseng discovered the promise, and Keith Whitelock and John Harton were very keen to see where the promise would actually be ranked, and that's how the list started, and obviously has grown and grown. What constitutes the list? Well, there must be some evidence, and with these, especially the older stones, there's lots of information that's obviously been missed and whatever. So we try and get as much information as possible. I believe there should be a distinction between gem and industrial diamonds. And of course, there should be a starting point. Originally we started at 300 carats, but so many stones have been discovered recently that are huge. And then there's another question, at long discussions with Prof. Steve Haggerty, should carbonos be included in my list? Not. Thanks. You can go, Tanya, thanks. Okay, so some basics of the list. The original list just had a one-pager, which was just all the biggest, but we've started breaking it up into different areas in terms of gem or whites or yellows and browns, etc., etc. So there are many pages in the list, and you'll see as we go along. Time doesn't allow us to get too involved with the list, but after the course, I will arrange with Tanya and John to everybody that's on the course that's interested to provide them with a proper list, an updated list. And then just looking on the left of that picture is a beautiful light brown Saroa from the fantastic Karowe mine. That's 472 carats. Could it have been 500? We have these problems. Sometimes diamonds do get damaged. Okay, so in the world of diamonds, bigger is better. And we've always said that. And if you look at that wonderful photograph, including the diamond, it's really the most stunning stone bought by De Beers in Mabuji mine in the old Zaire or Democratic Republic of Congo. De Beers and Steinmetz shaped it into this incredible 200 carat pair, and it just illustrates the whole world of these clipper diamonds. Bigger is better, and that's a beautiful D-color flawless stone. What started it all? Well, many centuries ago, of course, these big stones came out of India. The Koino came out at 793 carats. It's a beautiful 105 carat now. Just an incredible stone. And then followed by the 17th century, the Orlov. A lot of history in this stone. It's been called the Great Mughal as well. 787, huge stone, followed by Tavernier. Lots of history, lots of interesting points, lots of debate over the stone. Was the Orlov really the Mughal? But most historians believe it was, and I follow that. And then, of course, what changed it all? We had the big stones in Brazil and India and whatever. And then, of course, the South African diamond fields arrived, and these huge stones came out, 995 carat Excelsior. But then, of course, in 1905, that huge Cullinan came out, and it just obliterated any record that was there. I don't think it could be comprehended then. I think even to this day, I don't think we can really comprehend something that size. Big question, would we ever find anything bigger than the Cullinan? I think many people do doubt it, but you've got these large circuits recovery circuits now. You've got this fantastic XRT X-ray technology. You still have Cullinan, you've got Karowe, you've got Letseng, Zhuaneng, possibly even Arapa. And then, of course, Steve Weatherall's Le Carper, the Lulu project, and Matai. You never know, eh? That's what started it all, this magnificent stone. And we've seen this picture time and time again. Unfortunately, there are very few quality photographs of this, given the timing. And the stone was gifted to King Edward. The two main stones, anyway, Star of Africa 1, or the Great Star of Africa, at 530 carats, quite incredible. And then the lesser star, the Cullinan 2, weighs 317 carats. Just this huge, huge stone. I mean, can you imagine 621 grams? You know, if you take just a tub of margarine, for example, you know, 4 inches or 2.5 inches by 2 inches, just incredible. There's been a bit of work done on how big the Cullinan could have been. Wilson suggested that it could have been about 8,300 carats. In my studies of the model, and a few of my co-workers, we believe that it was rather around about 6,000 carats. But be that as it may, it's still a huge, huge diamond. And of course, that's a great star, just the most incredible stone. I had the privilege in having a private audience in the Tower of London with the commander of the guard, and it was out the scepter because they were having it repaired. And it's just the most incredible diamond in the world to view. So I was very, very lucky and spoiled then. And if you take it 1,063 carats out of the Cullinan, just a huge yield. Just quite amazing. Okay, so this is what the basic list looks like. Very simple, straightforward ranking, a name for it, the carat weight, when were they discovered, what country, what type is it, seeing that we've been through all these types, and then of course color and type in terms of industrial or cleavage, etc. And there's two, the next slide is the same, going up to 59 on my list. There isn't really time to go through it now, but once the students or who's ever interested get it, they can actually go through themselves and just see in terms of size or in terms of year, and we'll go into that a bit later in the show. So some stats there, you know, it's just quite amazing when you look at that. There's only 5 stones that have been discovered over 1,000 carats. I suppose if you included the Sergio, the big carbonado, but I don't really include that. And if you think that Cullinan was 3,100 and the next biggest, the Sewela, is 1,700, there's still this huge gap to cover. And then just some stats on how many stones there are, between 900 and 999 carats. But the most important stat really for me is that since 2015, Botswana has produced 10 of the 17 largest recovered in that short time, and Karowe 9 out of 17, just quite amazing. And again, we go back to Andy's presentation where you look at the most of the stones are from Africa. And then why do India have so few? Why doesn't Russia and Canada have so few? So some good questions for the geos there. Because the new kid on the block, the giant, is Sewela, just the most amazing stone at this huge 1,700 carats. It looks like a piece of bort, but I have seen photographs. We're showing the amount of light in the stone, and I think we'll still be surprised once the stone is actually polished and it take away the black outer, which you'll see in the next slide. So it was sold to Louis Vuitton, and HB in Antwerp will be polishing it. And obviously they're spending a lot of time in mapping it. It's very difficult with the coating to actually see what's exactly inside. But I believe that they will peel it, if that's the right term, and slowly work away until they see exactly what is inside. But just something quite amazing. And what we're seeing with the Karowe, that a lot of these giants are actually lower quality diamonds. This stone is what we call a cleavage. It's very, very cracked. but there are definitely pieces of gem material within that. And I think if you had a strong light behind that, you'd probably be able to see. So the stone will be broken up and the polishable pieces will be taken out. The next question is the stone actually type 2A, the material that will come out? And then, of course, the Lesedi, just the most incredible stone, probably as celebrated as the Cullinan, just an incredible diamond. Interesting that it was found very soon after Lucara put in their Tomra. Just absolutely amazing. And then, of course, bought by Graf with the most incredible 300 carat emerald to come out of it. All very nice with their own certificates. If you go to the next slide, there were 66 stones cut out of it, and everyone has got a unique number and a special certificate from Graf and by the GIA, quite celebrated. I think any lady would love to be able to hold something like that. And then the surprise was the big unnamed De Beers, just incredible stone. I think most of the geos watching this will agree with me that they've been waiting for a big one to come out of Zhuaneng. And obviously the De Beers XRT machines are working just fine, looking at the results. It's an amazing diamond. It's the biggest diamond that De Beers have announced in many, many years. If you go to the next slide, you'll see the dates. The millennium in 1990, the golden jubilee in 85, and the centenary in 86. So De Beers hasn't had a extra ultra large stone for a long time. This stone is a really giant, and 73 millimeters long is just amazing. Thanks, Tanya. One of the next big clavages from the Karowe mine at 998. Lovely photo from Dr. John Armstrong, just with a suite of mostly clippers around it. Just the gem content from the Karowe mine is just absolutely amazing. And as per the previous large clavage, they will break this up and they will polish out what I believe will be type 2 pieces as well. Then one of the older stones, one of the famous stones that came from the Jagersfontein mine, absolutely incredible stone. Very interesting for me because it's actually a G color, owned by Muad, the jewelers now. And it's a G color. And the interesting thing for me is that it's not very seldom that we ever get a G color in the type 2As. So I'm wondering if it's a type 1AB, but unless we get the stone, we wouldn't know. Also, one of the oldies, one of everyone's favorite stones, the Star of Sierra Leone, just incredible, beautiful. And I think you can see the scale with the former president holding the diamond. This is still the largest alluvial diamond ever found. Then, of course, Letseng found this fantastic monster of a stone, absolute beautiful stone. Some incredible photographs by Jem in Antwerp. I've held this stone. It is just the most magnificent stone. Next slide, you can see some more different views of it. It's just incredible. When you think of $40 million, it's huge. And that's what the Clipper diamonds, I think, are all about, is this huge value, beautiful diamonds. Then also, unusual stone is the biggest colored diamond ever found. Huge piece. I mean, just the polish, just 407 carats, just absolutely incredible. Lovely color. It actually appears more brown, but the GIA has given it fancy brownish yellow. So it's still regarded as a yellow diamond. The necklace is valued at 55 million US. So quite intriguing. Then back to another list where I've taken the 30 largest diamonds ever found, looked at them in terms of color and in terms of type. And later when you get the list, you can have a good look for yourself. But just a quick glance at the list, overwhelmingly type 2As. Okay, the Cullinan Heritage, magnificent stone. Love this photo from Petra with the broken pieces, well, pieces that were found at the same time as that. Were they part of it? You can be the judge. But again, you know, the huge value, 35.3 million bought by Chow Tai Fook. And on the next slide, you'll see the magnificent jewelry that was made out of it. Centerpiece is 104 carat D flawless round. Just the most amazing. Okay, back to the list again. The white type 2s. Again, you can see mostly African and just the sheer size at the top. And of course, you come in with the Lesedi and the De Beers diamond, 1,000 odd carats each, just amazing. And then if you go to the next slide, we've joined a list where we put the yellows and the browns together. And if you think there's 59 diamonds on the main list, only 13 are yellow and brown. And there are a few, I know John Bristow's always interested in the biggest octas. If you look at number 8, the Fenta diamond was a big yellow octahedron from the Northern Cape in South Africa. And then just looking at this, the clavage and industrial list put together, obviously topped by the Sewello. But if you look at 4 and 5, those are 2 industrial stones. There's an unnamed Russian stone, very little information about it, but 888 huge bought. Russians very seldom produce anything over 300 carats. So it's quite amazing that they recovered that. Then one of my favorite stones that I used to play with, I suppose you could say, when I still worked at De Beers, the 616 is just the most amazing stone. I believe it's a type 1B. It is a fancy yellow, the biggest fancy yellow in the world. It has many inclusions, and De Beers decided they would not sell it or polish it because it's the largest octahedral diamond in the world. Of course, you can see it is slightly resorbed on the edges, so it does have a dodec part to it, but still mostly octahedral. And of course, you can still see it in Kimberley at the Open Mine Museum. Okay, my favorite diamond, and one of the diamonds I worked with when I was still with De Beers, Golden Jubilee, is just the most incredible stone, 755 carats, found in the then Premier Mine. Just absolutely amazing color, and the biggest brown type 2 ever discovered. Just incredible color, just absolutely amazing. And then just for interest's sake, there will be a separate sheet for carbonados on my list, but they won't be included. But just interesting is from Professor Haggerty, 4 of the 5 largest diamonds found in Brazil were carbonados. And if you think that the Sergio was 60 odd carats bigger than the Cullinan, it's a huge diamond. Unfortunately, it was sold to a London broker who sold it on to tool makers, and the stone was crushed up into 3 to 6 carat bits for specialized industrial tool bits because the carbonado is so hard. And then the biggest one, which is subject to debate, is the Spirit of Grasonio, which is found in the Central African Republic. Still some debate on whether it is a carbonado gem. You can move on, please, Tanya. Okay, so there's a list. Not much is there. Those most of what I could find. But interesting stones. If you look at the next slide, it shows the Enigma, which was a polished carbonado, which is sold for over $4 million, possibly about 800 carats in the rough. So quite a serious diamond. Unfortunately, there's no information as to where it was found and when it was found. But I think it's the Central African. And then the next slide will show the Spirit. Just an amazing diamond, polished in the Mogul fashion. The older people in the audience will recognize the tennis player and his wife, Mrs. Henry Lecan. She modeled the stone for Grasonio, but absolutely magnificent. I'm not sure if the ring is the right idea, but just to show the sheer size of the stone. Okay, so this is the list from 2000, going on size, the biggest stone since the year 2000. The list is just two that I've drawn up where I show that by year and by size. And again, you can see Botswana very prominent. If you then go, sorry, Tanya, one back. If you then go from a year perspective, 2002 was when the win was found. Then the big Angolan, Star of Stanley Ho. And then there was a 3-year hiatus, and all of a sudden the Lesotho Promise was found. And then you can just see how all these years are compressed and how many stones were found from 2006 when Letseng opened. And then, of course, with Karowe opening shortly after that, plus with the modern technology of the XRT systems, etc. This is just a further extension of that, where to show from the year 1970 how few stones there were until you got to the year 2002. Again, a small hiatus, and then all of a sudden, with the startup of the Letseng mine, you had all these incredible stones coming out. Followed in 2015 with all these stones that came out of the Karowe mine. So back to the Cullinan mine. Wonderful diamonds. Just a nice photo from Petra with the 200 carat next to the legacy. Lovely, very clear pictures of beautiful clipper diamonds. Then back to one of the older stones, one of my favorite photos for diamonds. When I was in the factory learning how to split the stones, that's how we did it. And then on the stones that had many cracks, you had to mark it out and label it, and then try and work the polished yield from that. So fascinating photo for me. Of course, in those years, there was no Saurine or Galaxies and that. A beautiful diamond. Then the second biggest stone found in Angola, or second biggest documented, I should say. This is found by Lukapa in the Lulu project. Fascinating mine. We know they're very, very close to the kimberlite. All the large stones that I've studied from the Lulu project have no transport abrasion or any wear on the diamonds. So the stones haven't moved very, very far. So I think the kimberlite will be very, very close. Beautiful diamond, polished in Dubai, 22.5 million. Again, it's got to be a clipper. Then just following up on Andes, on these Cullinan-like large inclusion, pure, irregular and resorb stones, just absolutely amazing. There's a list of the top 24 white stones. The chances of them all being clipper diamonds, I think, is very, very strong. And perhaps Evan or Stephen or one of those would be interested in having a go at those. Of course, we can't get them to examine them closely. We can only work off photographs. But I would imagine that the majority of those 24 would actually be clippers. And I think you might have seen this photo in a previous presentation. But again, just to look at the models, I think the big one in the center, it's 91 carats. I think Farnes Verleuen called it that shape a potato. But you can see some of them are very, very blocky. Some are elongated, and all are irregular. And then occasionally you will find an octahedral face, and you never get type 2s that are octahedral. But I have seen octahedral type 2s where they've actually been broken along the octahedral faces. Okay, then also one of my favorite stones, because I worked on it with my mentor for many years, Gabby Tokowski, an incredible diamond. just polished by the stunning team led by Gabby, some of the top English polishers, and then Wim Davy Duplessis did the final brilliant earring. Absolutely magnificent stone. If you look at those dimensions, it was also just a super, super stone. A lot of work went into it because it was a highly stressed diamond. And I'm sure the students can do a bit of research on it and find out about it. Amazing stone. We know that De Beers has sold the stone. They don't talk about these things, but apparently it was sold for somewhere in the region of 100 million. And that's huge money. And also one of my favorites, because I was there when it was found, the Promise found in the satellite, like most of the big clippers in Letseng, just started this new era of large stone discoveries with Letseng being reopened, followed by the Karowe, followed by this new technology. We're now seeing it with Lulu and with Zhuaneng, this amazing technology which is helping us find these big stones and not crushing them. Graf paid 12.6 million for it in 2006, which is a long time ago, and made this incredible necklace. And this was the first piece where all the stones that were polished from the stone were put into one piece of jewelry. I believe that Graf was looking for about 78 million for the necklace. So again, huge money from this beautiful clipper diamond. Okay, then looking at some of these, let's say, giants, obviously all clippers, just amazing, especially having been at the mine when some of these were found, like the Lesedi and the Star, wonderful diamonds. And again, you can see that some of them are very, very blocky indeed, and some are just slightly elongated, but all D-color material, amazing stuff. And then another stone I've worked on was a wonderful diamond to work with, bought by Graf. This was the Mayor Prosperity, which was found in the first few days that they did their trial mining. Absolutely miracle of nature, this. Just incredible, very, very flat diamond, but Graf polished a 102 carat pair out of it. Just absolutely amazing, beautiful stone. But this is an E color, not a D color, but yeah, absolutely beautiful stone. In the Peace diamond, very interesting, found by artisanal diggers. Quite a history to go with it. They had an auction in Sierra Leone, and I think the winning of the highest bid was 7.5 million, which was rejected by the government and the owners of the stone. And when they eventually did sell it through Rappaport's auction, Graf paid 6.5 million. I think this is possibly the only non-clipper diamond of all the giant diamonds that Lawrence Graf has bought. It's light yellow. I think there'll be some interesting pieces to come out of this. Then just a list on the non-African countries, obviously India, Brazil, and Russia and Canada. Again, not many. If you look at 15 diamonds out of the list of 59, which shows how it's biased towards Africa, and I'm sure Andy and them will come up a reason of why we have so few diamonds from the north, especially Canada and Russia. And then on the right, the beautiful wind diamond was found in the Amazon alluvials. Beautiful stone, polished a 230 carat pair. I think it's the second largest pair in the world. And then quite a busy slide with all the African stones, 44 out of the 59, just amazing. And of course, South Africa and Botswana really appear very, very strongly on this list. I would imagine that Botswana is now on about 7 are the biggest, or no, 10 are the biggest, and South Africa on 17. And I'm sure with the rate of recovery with Karoi and now Zhuaneng, I think that list will change quite quickly, unless Cullinan comes up with some more giants. Okay, then we get to the most difficult part of trying to do a list like this. Is there's information out there of stones that were found, but there's no information, and a lot of it is hearsay, that, you know, there was an 800 character that they found in Angola, or this stone that De Beers produced, or whatever, but there's no solid evidence that these stones ever existed. And for example, if you take, there's a 700 character, which was supposed to be a light blue. There's only one reference to it, and I've spoken to many of the diamantaires in Antwerp, and they don't believe that that stone ever existed. But again, if you go into the historical side, there were big stones. A lot of them were the borts and these poor quality clavage stones, and they were just never ever recorded, or any information was written about it. So if you concentrate on these points, that we know that there were these large stones in India and Brazil centuries ago that was smuggled out of the, stolen from the temples and smuggled out of the mines, and even from the African mines as well. Many of these industrial pieces were never ever recorded. There might have been a note in the mines record, but there was no other record of it. And once it was polished, broken up, there's just no further record. And of course, to this day, we know that there are diamonds being broken on the mines. And when you have these giants, there's a strong chance that they will be crushed. And we won't even have evidence of it in certain cases. And then, of course, these very old records, which are referred to here on the left, it does need follow-up. Somewhere there must be something written about it. But that will take a bit of time to do all the research for that. And then I'd just like to thank Mrs. Debbie Barn, Drs. John Ward, John Armstrong, Dr. Mike DeWitt, and Dr. Patty Lawless for all their help and their support over the years, and also helping me keep the list going. They're very keen on all these large stones. And then special thanks to Brandon the Brain from GEM and Dr. John Armstrong for those extra photographs that they sent to me. And then, of course, I've always dedicated my list to my mentor, Dr. Derek Robinson. Worked with him for many, many years in De Beers. A wonderful, wonderful man. And then once the list is sent out, all the references used in this presentation will be on the list once it gets sent out. Thank you very much.
Thanks, Ray. That was tremendous.
Thanks. Went a bit faster than I anticipated.
Yeah.
But yeah, it's a fascinating world of these large stones, and this whole correlation with the clipper diamonds just add an extra dimension to this list as well.
Okay, Andy, do you want to drive the questions?
John, may I ask a question to Ray?
Yeah, go for it, Mike.
Hi, Farnus.
No, it's Mike DeWitt. Ray, may,
hey, Mike, sorry.
may I suggest, Ray, that with these blue diamonds being so incredible, special, that you start a new list just with blue diamonds and see how far back you can get with that one.
Yes, I do actually have a basic list, but I haven't updated it, especially with after those fantastic Cullen and Latapa blues.
Okay,
So, yeah,
that would be great to see that as well. That's
on the menu. John and James Campbell have a request that I do some research on the large alluvial octahedrons that have been found, and that's also on the list. But it's a time issue, of course.
You got the weekends.
Yeah, thanks. I'll have to come and visit you.
Ray, a question from me. On your lists, what is the proportion of kimberlite diamonds versus alluvials in this list? And to a further question, in the ones recovered from kimberlites, do you see in the photos or the ones that you've personally looked at evidence of diamond breakage or plant breakage?
Yes. Yes, there are quite a few of them have shown breakage, like the photo of the 470. The very interesting one, of course, is the Suelo and the Constellation. There is a paper on it, and I'm not sure that it's been finalized by De Harens, where there's a possibility that it was one big diamond of 2,400 carats and broke where the diamond was zoned. The Constellation is a type 1AB diamond, while the Lesedi is still a type 2A diamond. So there might have been a weakness where the zoning was. The diamond, the Constellation was certainly found with 3 other pieces, and you could see that in De Harens' paper. So yes, it does still happen, and I'm sure in the past, we know that there have been quite a few of these large stones broken, but once it's broken, that's done. It can't go on the list and say, well, it could have been this.
Ray, you mentioned that the 616 octahedron had inclusions.
Yeah.
Are they clear enough to see whether they're eclogitic or periditic or...
From what I can remember, I only observed sulfides in that stone.
Oh, okay. Yeah. Thanks, Ray.
So that would be that would be interesting.
Go ahead. Yeah, there's a question from one of the students who sort of dropped out for a few minutes about the black diamonds or carbonados. Why don't you just quickly recap on that for them?
Okay, so the carbonados, and they should read Prof. Steve Haggerty's paper on that, are deemed to be extraterrestrial. And that's why I haven't included them on my list of mantle-derived diamonds. So again, they are very hard industrial diamonds, but some of them have an inner core, which is totally black. If you saw the photo of the Enigma, has got a sort of grey, browny sort of streak to it. It's not pure black like the Grasonio is.
But
there's
quite a lot of quite a lot of those black diamonds, even smaller ones, are black because they've got, lots of black inclusions or sulfides and stuff like that.
Yeah. Look, black diamonds are actually... Black diamonds, as in fancy black diamonds, are actually very, very rare. And that's why they are so expensive. And when you start looking at a 1 or 2 carat fancy black diamond, you could be talking $2,000 a carat. So, but they are rare. All my years, the last 5 years, looking at all the alluvial productions, for example, I've come across about 4. So they're pretty rare.
Okay. Right, and just to throw sort of a very broad comment question into the mix, and it's for you and Andy, and I see Herman's on the presentation and all the other petrologists. I mean, it's fascinating. If you look at, these big diamonds, I hardly saw any mention of big diamonds out of the Northern Hemisphere. So if you go India, Africa, obviously, and then Brazil, all in Gondwana, these old Britonic areas. And Aussie, as always, the Australians are the odd one out in this case. But just these amazing number of big diamonds, and we talked about it, I think, yesterday or the day before, Ray. I think Grib in Russia has produced a few big diamonds, but very, very few others. If you look at the the Siberian pipes, although I remember early on Barry Hawthorne, and I think Steve said the same thing too, there was a lot of breakage there where they used rod molds. But, you know, any comments on that?
Well, the interesting thing is that having looked at a number of the group productions, and especially when they've had their type 2s, beautiful stones, and no reason why they shouldn't be clippers as well, but it's quite rare. But they actually produce some big stones between 100 and 300 carats. So there's no reason why they couldn't come up on the list. Why the main Russian mines to the north, north east, you know, why they haven't produced anything of note is anyone's guess. I'm sure maybe Herman could help us with that. But even Canada, you know, Divik has produced a couple of marvelous type 2s, which could quite easily be clippers. But, you know, if you're taking 15 plus years, they've only produced 2 or 3 type 2 diamonds. You know, where did they come from? Was it just a different pulse, or where did they come from? Herman, any comment on that?
In the case of Divik, those big stones were actually accidental recoveries. They would have been crushed if it wasn't for their shape. So, you know, the industrial processing that was going on at Divik, and I don't think Divik has installed an XRT circuit yet, because it's about to close. So those big stones were definitely accidental recoveries.
Yeah, but again, you know, if any of them were broken, and I worked there for 2 years, and in my 2 years we only found one, which was a 78 carat, the most incredible, could have come from Cullinan even. And all the time I've never seen any other type 2A pieces, but there was the Foxfire, wasn't there?
Yeah.
Okay, so they are there. It's just, you know, not very many.
Yeah, just so random though. You know, and again, if you look at the list, you know, only 2 stones are from Russia, of the large stones, the 888 bought, and then that 400 carat mackerel. You know, there's nothing like a clipper. And then of course the only one from Canada is the fancy yellow. So,
Ray, sorry, I had 2 different questions for you. The one is a request that you actually, on your list, you actually specify the source, not just the country, because it turns out that it's quite important. Maybe you didn't show that column. Are you actually recording the actual source if you can?
Yeah. Yeah, I will do that. Thanks for that. The information is there. Some of them, of course, it comes from Kimberley. Which of the 5 Kimberley mines produced, you know. So some of it is a bit difficult, but yeah, I will do that and specify the actual mine.
Yeah, because that's actually, you know, from a genetic point of view, and whether it's associated with megacrysts or other bits and pieces, actually important information. The second question was, if you had to estimate the annual proportion of annual rough diamond trade, let's say it's $8 billion annually rough trade, maybe that's sort of an estimate number. If you have to estimate the proportion by value, that these large stones, let's say $2 million a piece rough, is in the trade on an annual basis, what percentage would that be in your estimation?
Starting at what size though, Herman? Starting at 100 carats or?
Well, let's say the individual pieces are selling at $2 million a stone. You know, stones that are selling for $2 million or more.
Yeah, I'd say it's quite a small percentage actually. If you're talking Letseng, and if you're talking Karowe, totally different thing. You know, if you look at, for example, the huge output of carats of the Zhuaneng mine, you know, even 1,000 carats a stone, you know, will obviously make its presence felt, but it's going to be very small in the annualized revenue.
Yeah, but it's interesting. It's an interesting question, Herman. If you actually look at, you know, average Botswana production, if you believe it, and I think, you know, the numbers are reasonably okay compared to, say, Russian production, but, you know, there's quite a significant difference. And I suspect, I mean, we over the last couple of years have done some work in Botswana, and you know, I think we underestimate, and maybe I'm talking, you know, you the expert, Ray, but I think we underestimate that, you know, the sheer quality of joining. I mean, if you look at a run of mine, you know, sawtooth parcel of joining, I mean, it's just amazing compared to, you know, just about every other kimberlite that you look at.
Yes, for sure. No, absolutely. I'm not privy to that information, but if you had to look on two different mines, for example, we would find all these clippers for Letsang and Korowe, your special stones that you're referring to would probably account for 70% of the revenue.
Yeah.
That's
yeah, there
totally
you go.
different.
Yeah.
But they are small productions compared to like the Zhuaneng. It would be very difficult once you take all the small diamonds produced by Zhuaneng and all the industrials and the rejections and the clavage, it's going to pull that price right, that value right down. But yeah, interesting question.
Okay. Right, we're going to keep moving, but we also have a question here from Bill saying, Ray did not answer the question about roughly the ratio of alluvial to kimberlite recoveries for the diamond.
Yeah, sorry, we got a bit sidetracked now, Craig. Probably it's 1 in 10 is alluvial. So that'll come fit back in with Herman's question of having the precise location. Look, many of them, like the big Sierra Leone stones, were all found in the Dominco alluvials until recently. So there's what 4 stones already with the Woi and the star. Yeah, it would be interesting. And there's a couple of the South Africans, like the Fento was an alluvial. So that'll be the next project, is to tidy up the list and have this information on a more definite basis for you.
Yeah, I agree. I'm being a bit pedantic, having worked on the alluvials. I mean, if we recorded all the big stones sold out of Kimberley and the tender houses, you know, and from, say, Hopetown to Douglas to Prieska, and Mike will have some info, you know, the stuff that even came out of the Vaal River section. I think it'll be a fascinating study.
Well, if you take the alluvials from 50 carats to 300 carats, is a fascinating, and I mean, you know, the dollar per carat is just quite incredible. Eh?
Yeah. And what about Namibia? I mean, Southwest Africa. What's the contribution from there, from the coastals?
In terms of large stones?
Yeah, there are not very many. There's not many big stones, Bill. I mean, there have been some big. There are a couple of. Ray will again be aware of them. They're not sort of talked about big stones out of the lower Orange River.
Yeah, well,
The biggest.
we do know that there's a couple of plus 100 carats have come down the Orange River.
The biggest stone on the west. The biggest stone in Namibia was 211, I think. And something, and this biggest stone on the Nakwa coast was also just over 200. Okay, so I really want to walk through some of the exploration steps that one needs to take and one needs to think about as a young geologist, for those who want to get into the exploration field, particularly for diamonds. And I think John Bristow made the comment quite often that we do need new blood and new ideas in this business. So let me take you through some of the thoughts and ideas on exploration and how we should go about it in the future. Before doing that, it's important to look at a bit of the history of the production and the production profile of diamonds globally over time. And it's all driven by exploration discoveries. We see various kimberlites starting in the 1960s, in Russia, Iraq in the 70s, Huaneng, and all these discoveries added to an enormous increase in production of natural diamonds for consumption in the market. But I guess the peak reached in about 2005, sitting around 170 million carats per annum, reduced. Firstly, because we went through some financial crises globally, but also because many of these discoveries were reaching the end of their life. And as was mentioned early on, we see Argyle, a big producer of carats, closing recently. So the trend is really down from the 170 million carats per annum. So it is time that we make a look at new discoveries, and that's really what we need to think about for the future. I just put down here a couple of books actually that always interested myself, and barren lands was already spoken about early on in the week with the discovery of the kimberlites and the diamonds in Canada. The Diamond Seeker tells you about John Williamson's discovery in Tanzania, a very interesting read. We put together recently a book on prospecting in Africa by De Beers geologists, and how they lived and how they worked through their programs. And another interesting book is Robert Friedland's story on his various discoveries, but particularly this one on Voisey Bay. But the trend of all these books is really the fact that the discoverers of all these various deposits were people that had incredible enthusiasm and interest in exploration. And if you don't have that from the start, I don't think this is a game that you want to get involved with. You have to have that interest and that tenacity to enjoy and find the challenges exciting. So just to go back to the discovery issue, and we see that the 2005 high that we had at about 175 million carats. The only sort of light in the tunnel at the moment is the discovery in Angola, which Herman Gruter spoke about yesterday. But other than that, the trend is still very much in a downward way. But it's not just for diamonds. We see this trend in many other commodities, gold and copper and so on. There has to be a new take in exploration to try and find new deposits. In terms of the exploration for kimberlites, and I've put it 2 slides here, 2 graphs showing the number of diamond-bearing kimberlites found per decade, and a definition of a diamond-bearing kimberlite is anything over a carat a ton. And it just shows you how steady it was up to the 1950s when the Russian discoveries came onto the scene, and then Botswana, and then Argyle and Canada. But since sort of 2000, there's been a really downward trend of this, of the discovery of the number of kimberlites with diamonds being discovered. And one can do the same thing by adding all the totals of the hectareage of the surfaces of those kimberlites, and we're really running out of new discoveries to come onto the market. There are other reasons why we see this decline. It's also many of the mines are getting older. They have to go underground, and going underground is a major shift in the amount of material that one can extract in comparison to an open pit mine. So it becomes costlier, becomes more difficult to get out the tonnages that one requires. And eventually, the economics drive the closure of such mines. It's interesting if you look at Kimberley, those mines were started in the 1870s. 5 major mines at the time. 3 of those kimberlites are still mined today at quite considerable depth, but it certainly has reduced the tonnages that are coming out of those bodies. In addition to the kimberlites, we see a major reduction in alluvial diamonds being produced. We had the Marangi deposits in Zimbabwe that were running at 10 to 50 million carats per annum over a fairly short period of time. That's reduced now significantly, and the estimates are that it's sitting around 1 million carats per annum at the moment. The Macquarie is closed down. We see the reduction of the onshore Namibian deposits. So overall, really see a major reduction in diamonds coming onto the scene. And this was mentioned yesterday as well, the majors and the juniors, who's doing the work, who's putting the risk money up front. And it's becoming more and more the juniors who are putting up a lot of the risk money in the hope of attracting majors in further development of new projects. So I'm not going to go into detail on this. We spoke about this yesterday, but it really is quite interesting to see that the supply and demand is very much out of phase, and will continue to be so if we don't find something new on the horizon. So if you look at the exploration pipeline, it's made up of various stages, starting with target selection, going into some regional sampling, some follow-up sampling, geophysics, which was discussed in detail yesterday, drilling, evaluation, and then into mining. The risks at this early stage are high, but the costs are generally low. So it's a stage where one can put some money up front, try and develop some new targets, and see if this can move into a project that has more potential, but also then becomes more expensive to develop using more sophisticated technology to move it along. A typical sort of flow chart of exploration, which is based really on Margaret Muggeridge's work, is to start with target selection. Where would you put your money to try and locate a deposit that's worthwhile exploring? And there are various issues that one has to think about. The presence of cratons, so the geochronology. You need to look at. Is there any regional geophysics available? What's the geology like? Are there cover areas of younger sediments than kimberlites that you may expect? What is the structure like? Are there structural traps that may host kimberlites to come through? And then one has to think very carefully about the geomorphology and the rheology. What are the soils like? What is the drainage like? How do I develop a program that would cover these things? And in most cases, it is really worthwhile to do a field visit once you've identified an area of interest. You want to know what is the access, what are the logistics like, and what is the drainage development, what are the trap sites like. So these are things that one needs to sort out before you start deciding what sort of sampling one is going to do, what size samples you're going to take, what are the sample intervals, what are your screen sizes that you need to think about. So those are important considerations, which then link also, how am I going to treat these samples? How am I going to concentrate them? Is it in an area which is difficult to get in and out of? So those are aspects that really have to be mapped out before you actually start doing any work. You then will get into your, once decided how you're going to tackle the area, you get into your regional sampling. It's either stream sampling, low sampling, or even till sampling, as in Canada. You would then move into detailed sampling. You would look at some minerals that you may find, look at surface textures and mineral chemistries. You then may decide to start looking at airborne surveys to hone in onto particular areas that may have had some interesting surface results from surface sampling, and then go into ground geophysics and drilling. So it's a fairly a very standard way of looking at an area, but there are no such things as shortcuts. There's no such thing as going from detailed sampling into drilling, because that ends up in tears. You're missing targets, missing drill targets, and perhaps walking away from areas that have not been properly investigated. So be careful how you move from one stage to the next stage. Be careful that you don't take shortcuts, because that really ends up in problems. In terms of the target selection, and we've already spoken about Clifford's rule in the 1966. In the 1960s, he was the first one to identify the relationship between diamond-bearing kimberlites and cratons. It's a fairly well-established fact now, although there are some there are areas where perhaps this doesn't work too well, but in generally, that is the way to look at new areas. One can think of, are there any diamonds in the areas? Do we have any ideas on what type of diamonds these are, and maybe even some diamond ages? That's all very useful information when you do your target selection. What's the level of erosion? What's your cover? What's your soils like? Are they likely to give problems when you do sampling? And are there any major structural discontinuities? Do we have any idea on known kimberlites in the area that have perhaps some ages? And then what type of kimberlites have we got? Is it group 1s or group 2s that may have different mineral that they produce? So a lot of these things can be done on a desktop, and one can already do quite a lot of this selection of areas from available information that is on the internet or in books and papers, and it's worth spending quite a bit of time to get your target selection fairly on a solid basis. So what do we look for when we go out sampling? These are the sort of minerals that are part of our strategy in terms of looking for kimberlites. Unfortunately, they never look as fresh and sharp as they are in this picture, but these are the minerals that are pathfinders. It's the garnets in red, the chromaopsites in green, the ilmenites and spinels in black, and then obviously there are occasionally you would find a diamond in your samples. Now, I was speaking about group 1 and group 2 kimberlites. I think Johan Stephen has spoken a bit about kimberlites, but they tend to give you different indicator minerals, particularly with group 2s, where there is a lack of ilmenite, which is often a mineral which is extremely useful in tropical Africa, where garnets tend to be subjected to weathering, and the ilmenites are ones that are often survive these weathering processes. So let's just have a look at heavy mineral sampling, and I've put in a couple of lessons here. You either may be working for a junior company that's listed, or you may even be working for a major company, but it's very important to start recording exactly how you're doing your sampling, and what size intervals you're using and for what reasons. And it's good to have a look at the SAMREC codes in South Africa and the York codes perhaps in Australia if you're working there, to start getting a feel for the sort of things that you need to be aware of in terms of record keeping. Very important one. So what is the objective is in heavy mineral sampling is to try and recover kimberlitic minerals in order to establish areas that may be positive or areas that may be negative. At this stage, it's not, the objective is not really to find individual kimberlites, because that's not really what reconnaissance sampling is about. You can do alluvial sampling, stream sampling, loam sampling, or till sampling. I mentioned that before. You need to think of, are you going to take volume samples? Are you going to take weight samples? But whatever you decide to do, be consistent about it. Think about the cover and in terms of thickness and type, and what is practical in the area you're working. It's not very easy to take a jig into the field. You may want to really balance off the way that you sample against the practical accessibility of certain areas. And then, of course, it's the interval of samples. That's ties in with the cost against time. How quickly can one sample? You can sample an area on a very wide grid, but then you're likely not to find what you're looking for. So you need to think very carefully on your intervals, how you space your samples. And people tend to be much conservative, so they probably take slightly more samples than necessary, but that's probably better than undersampling an area. And then you need to decide, are you looking at very fine-grained sediments? Are you looking at coarse sediments? What are your mesh sizes that you're going to use in your screens? All things that sound very simple, but that make a huge difference in terms of your discovery chances. Now, I just want to point out a very simple thing. Make sure that you label your samples properly and clearly, and store your concentrates as long as you can. It's always good to go back to your concentrates. The sorters may have missed something. An example I always like to use is the discovery of the Kasai diamonds. The Kasai diamonds is in southern DRC. It's a massive alluvial deposits, which was found in 1909, but the license was given to a company called Foriminier, and they sampled it between 1907 and 1909 and found nothing. And they were running out of money. So they decided to go back to their concentrates, which they had stored in Brussels in their laboratory. And right enough, they found a diamond in one of the samples. However, as luck may be, that sample didn't have a number. It didn't have anything written on the bottle. So now they had to compare these samples, this sample with other samples that had numbers and where the concentrate looked fairly similar. And eventually, after 3 extra missions, they did find the sample site more or less, and found more diamonds, and eventually found this deposit. But they wasted quite a lot of time and effort by not having the right having a number on your samples. So in my view, any sample without a number, you may as well throw in the dustbin. Okay, so we will talk a little bit about sample collection, sample treatment, the sorting, and then the grain analysis, which I won't go into in too much of a detail. Sample collection, and this is a work that was highlighted by Maureen Muggeridge, who was instrumental in finding Argyle deposit in Australia. She sort of looked at the various areas and then tied in what type of soil, what type of sampling one would need to do in order to cover these areas. And it's just interesting to read her paper and her logic. If you have mountainous areas with good drainage, stream sampling would be the one to go for. It's quick and easy, and it's very representative of the area. Flat areas with no drainage would require soil sampling, and so on. Areas with a lot of overburden, you may want to think about airborne geophysics, but that could become very expensive. So these are geomorphological constraints that one needs to consider. You also need to look at the indicator minerals. This is a histogram of some results from tillite sampling, where most of the indicators are found in the finer sizes, and we see that the same in loam sampling. And this is not only a reflection of the concentration of indicator minerals in kimberlites, where their dominance is in the finer fraction, but also in larger grains break down in the weathering profile. So the finer you go, the more indicators one is likely to find. But of course, that comes at a cost, because finer grain samples are very much more difficult to sort and to handle. Some basic guidelines, which I just want to re-emphasize again. Reconnaissance work is not to find individual kimberlites. We're looking for clusters. We know that all kimberlites occur in clusters. So the reconnaissance work, the interval of sampling should be to find those clusters. an interesting comment always is that economic clusters were all found by sampling. You go look at all these diamond regions, all those were found by sampling. So target selection is critical. And, you know, as I said before, have a look if there are diamonds around. We see that at some of these other areas where where these big mines were found, Cullinan, Kimberley, the Moroa. These were all places where diamonds occurred in the area. But be systematic. Make sure that all the samples are labeled, and be consistent, either sampling with volume or weight. The way you take your sample, if you decide to do it one way, then do all the samples the same way, and try and keep it simple. These are just some basic guidelines. This is a graph of some orientation sampling that I did in the Kalahari. We were sampling for some areas that contained very fine-grained Kalahari sand, and this is a cumulative graph to show you the size ranges of this sand, which is sitting mainly in the 0.3 to 0.4 size fraction. So here we have to make sure that we link our size range of our screens to the size of material that we're going to sample. Very important. Then how are we going to take our samples? Are we going to take our samples using a spade or a brush, which can either be done, but if you decide on one, then stick to that for the same program. You remember that we are trying to do reconnaissance sampling, and we therefore sampling the deflation surface of the soil horizons. Those have the highest potential, or the highest chance of finding indicator minerals, heavy minerals, is this deflation surface. So by brushing, we're brushing off the deflation material, or by spading, we just try and keep it as a very shallow dig in the soil. There's an example of spading. There's about a square meter of material that's taken off, and you can see how shallow that material is. Again, focusing on the deflation surface. So be consistent. There are some other sampling methods, and I'll talk a little bit about scoop sampling tomorrow in Botswana, where they use the clinometers on a bicycle wheel to measure distance. These days, that's done a little more easier using a GPS. But that was one way of sampling. They decided to scoop sample and use a soil splitter in order to get a representative sample. And they would take a scoop every 600 or half a mile, and scoop, so regard that as one sample. That is fine, but be consistent on that one, and make sure that each sample has a location. That's I've seen quite often that samples come in with numbers, but then the location wasn't recorded. Again, these may sound simple things, but those are extremely important to do it properly. Stream sampling in the DRC. It's often quite useful to walk a stream up and down a bit and to identify a good trap site. This trap site here, there was a dolerite die cutting through. You can't actually see it. There's the top of it, but an excellent site for trap siting. So do a bit of homework on your trap site selection, and be a bit more flexible in terms of where you're going to take a sample. Very important if you want to pick them up. The importance of trap sites, again, is highlighted by Maureen Muggeridge, and it makes perfect sense that most of your good trap sites are sitting in your coarse gravels, while your poor trap sites, in this case, is very sandy. So these are things to look for. Have a look for percentage boulders, look for any obstructions in the flow that you may find in a stream, to optimize the chances of finding your indicator minerals. And then, of course, logistics plays a role. These were programs that we did in the DRC, and that hasn't really changed a lot. You needed pirogues to get across rivers. You needed bicycles or motorbikes to get through the forest. So there's only so much that you can carry for a 2 or 3 week trip There's only so much rice that you can take to eat for 2 weeks. But so do an orientation sample of the area that needs to be visited, and also have a look at the seasonality. There may be the rainy season is not a good time to be in the forest. It's swampy, difficult to get around. So choose your seasons if you decide to go into these sort of areas. This also leads to the fact that you can't take back big samples on the back of your motorbike. So you have to concentrate your samples, and that can be done fairly easy using hand gravitation, and can be done very effectively. Here are the guys hand gravitating screen samples. They turn the screen over on top of a piece of plastic bag, and you can see the concentrate that concentrated accumulated at the bottom of that screen in the center. That's this guy shows you how good a gravitator he is. He can concentrate that material. You may want to reconcentrate that 2 or 3 times to make sure that you've got most of your indicator minerals. But you scoop that out with a spoon, put that in a bag, and that's what you take back. So you don't have to take your whole sample back. You screen it, hand gravitate it, and take back the concentrate. So sample concentration. This is a photograph of the early concentration in Botswana, where they used gold pans, and there was no screening involved at the time. And it showed that that wasn't a very effective way of doing it, particularly having a lot of fines in your gold pan. So people went back to screen samples and using hand gravitation as a medium to or jigs to concentrate those screen samples and produce a concentrate. Again, I've showed you that with hand gravitation, very easy to do. And then you take out your concentrate by spoon, and you collect that as your sample that goes to the laboratory. There are various jigs that are available. This is a garage jig that was used on the West Coast quite a lot. It's a single-handed jig for small samples. But there are other types of jigs. This is called a Zambian jig. And this is very good for fine grain samples up to 0.3 of a millimeter, where the guy gently taps this rod here and moves this screen, which is sitting on in a cradle, moves it slightly up and down, and the gentle force of that tapping of the jig concentrates those 0.3 millimeter samples in the screen. This method was further mechanized by Demeda Torrey, by Fenter and Gavin Armstrong. They produced what we call the Fenter jig, and it's a screen that goes up and down in these columns, and at the same time there's an arm that turns them sideways, so you have a sideways movement and an up and down movement, and you can do 4 samples at a time, and it produces a very nice concentrate. However, you need to make sure that the jig is set up properly. It has to be horizontal and stable. Make use of traces in all these jigging exercises, and jig for an appropriate time. A similar sort of jig was used also on the West Coast, but also for bigger samples. It's called a pleats jig, developed in Namibia, and also a very effective tool to go for. Shows you some of the concentrates that one can produce from a mechanical jig. Very good concentrates in both cases. And you probably need to jig this sample. You can see there's still some dark minerals on the lighter side. So you scoop out this concentrate, rejig it, and you probably do that for 2 or 3 times and make sure that the traces are recovered every time that you jig. And later, there has been a development in producing micro DMSs, micro dense media separating plants, to produce concentrates for small scale samples. It gets more sophisticated. It's obviously you can't take this into the field. You have to set up it in a central treatment station. It costs more, and it's probably also very good for the finer fractions. But it shows you there are different ways of doing it, but it all depends on your budget. And and your logistics. Further concentration and treatment of those concentrates that you have now produced. If you're working in areas where you have lateritic problems or thick soil formations, you may want to treat your samples with acid. This is a photograph of the first acid plants that were developed by among others, Bill McKechnie in the field using oxalic acid. That obviously for environmental reasons has now moved into the more laboratory environments. But the objective is the same, is to clean your samples so that the mineral sorters can pick them out easy. We then move the samples through a heavy liquid, which separates the lighter material still from anything, depending on the liquid that you use, but generally anything heavier than 3. And then you may still, if you have a lot of magnetite in your samples, for instance, you may still want to put that over a magnetic separator. And the reason for all this is really to provide a concentrate to the mineral sorters who have to pick the minerals out of those concentrates individually, to make sure that she has the best opportunity and best chance of picking out these concentrates. So you've reduced the concentrate, you've cleaned it, and you're presenting the ladies with a good product. Just remember that you can go finer with your samples. Obviously, as I mentioned, you'll have the chance of getting more indicator minerals, but it also means there are many more grains to look at for these ladies under the microscopes. A size fracture, the number of grains per gram, you can see increases enormously if you go to the finer fractions. So that's the payoff. That'll take a lot longer to sort and will add to your budget both in time and in cost. These are the minerals, and we've been through it. I'm not going to go through it in any detail because I think people will talk about it at a later stage, but those are the minerals. They have different colors, which can, for instance, in your garnets, gives you already an idea of what sort of chemistry you're looking at, with the chrome-rich ones generally being more purple, the aglogitic ones being more orange, and then the chrome dioxides, the kimberlitic ilmenite, and the spinels. Those are the 4 species that is really looked for in southern Africa. In Canada, they make use a lot of using olivines in their samples, but these are generally not very well. They don't survive our rigorous weathering profiles here in southern Africa. In addition to the mineral species, you can then look at the surface textures, and here are some experiments that were done by the Russians looking at various mineral species and abrading them through a tumbler and trying to see how quickly a certain mineral erodes, and using that then perhaps as a link to how much transport a mineral has gone through. Just remember that this is in Russia. It's a cold climate. It doesn't have the weathering that we have, so that is fine for that sort of environment, but would perhaps be less useful in areas where you have a lot of diagenesis. Okay, so we've now done our stream sampling. We're finding on the left-hand side a couple of samples. The red samples are positive samples. So we now can do some more detailed sampling, and we can start collecting some samples that we can send for mineral chemistry. So we've highlighted an area of interest, and we've got quite a number of samples that we can now send for mineral chemistry, so that's very important. Now, are we going to take this thing further? Is the chemistry interesting enough to take it further, or do we walk away from this? So that would be in your follow-up stage. It's often useful when you get to that stage, the follow-up stage, to have a look at what is available in terms of air photographs. Or are there any features in the area? This is a photograph of a kimberlite called 18OP, and a photograph taken in 1964, where it produces a fantastic photo features. So Before any follow-up, go and have a look at some air photographs that might be available, or take a flip. It may surprise you. Finch had a very interesting photo feature, so did Arapa, which we'll see tomorrow. And many other kimberlites have features where the soil cover isn't all that great. You then may want to move onto geophysics. You've got an area of interest. It certainly adds to speed, but it also adds to your budget. And you would only fly areas that you have identified as interesting from your sampling. So this is just a photograph of the first airborne survey that was done over the Arapa province using a fairly antiquated machine, the Catalina from Canada. But as Gavin Shelf showed yesterday, there are lots of other ways of doing it, and it really depends on the size of area you want to cover, what sort of line interval you want to produce. So there are lots of things that you need to consider before you decide what type of airborne geophysics you're going to use. That's just a photograph of a kimberlite in Australia, and you can see that the background is very quiet. It's something that you need to think about. If you're looking for a heavy mineral anomaly in the banded ironstones, flying may not be the best way to go because you'll have enormous difficulty of identifying targets. So what is the background geology, and what sort of line spacing should I use for this? And this is a fairly small kimberlite, and it was found by 100-meter line spacing. Using 250 line spacing, what people use a lot, may not be the best way to go. You then go to ground magnetics. My rule is no drilling before you have done your ground follow-up. And this shows you, this is a magnetite unit in Botswana. That's the airborne survey, and this is the ground magnetic survey. And you can see how very much better defined you'll see your magnetite layers for drilling purposes. So my rule is you don't drill until you've done your ground magnetic survey. Physical properties of kimberlites, we've probably went through that with Gavin yesterday, and I'm not going to add a lot more, but it's interesting that your magnetic susceptibility increases with depth. So your diatreme and your hyperbisal zones are better defined than your craters. And this is also seen in your density, where your weathered surface or your sediments on top of your kimberlites have a lower density than your diatreme and your hyperbisal facies. So think about your erosions in the areas, what to apply in terms of magnetics or geophysics. Interesting, one can use magnetics and gravity over the same targets and start developing some 3D models. But that does require a full qualified geophysicist to assist in interpreting that sort of data. EM, also spoken about, Gavin, also a very good tool these days to use, particularly in Africa, where you have a weathered top zone in your kimberlites. Very, very effective. And then the last thing in terms of geophysics is looking for using ground penetrating radar. It's been tried and tested, not always all that successful, and it's probably more effective in your alluvial prospecting. In terms of drilling, again, it sounds a simple way of identifying targets. It generally is. This is one of the first drill rigs that we used. It was a percussion drill, and you have to be very careful how you identify your chips coming out of that. This was later improved by reverse circulation, so you didn't have contamination of different depths going down your hole. It's very important to confirm your drill position by ground geophysics. I can't emphasize that enough. I've seen too many holes missing targets and people walking away from areas which they felt were not prospective because they've missed the target. An important tool, and certainly in Central Africa, is a portable diamond rig. I used to be a great fan of percussion rig drilling, but I've changed that completely. Using this portable rig, we were able to drill lots of kimberlites. You end up with a good sample. It's relatively easy to operate. It uses no compressors, so like a percussion rig, and therefore a lot less fuel is needed. And it can be flown in by helicopter or even carried in places. And you get a direct sample which you can use for petrography and all sorts of other lab technology. So to me, that is really a very important one to go to. Okay, so the first steps of assessing your kimberlite, the logging, the sampling for once you've got your kimberlite, you do your petrography, and Johan would have spoken about that in a bit more detail. It can tell you already something about the potential of this kimberlite. You then take your core and you take some probably about 20 kilograms to get your indicator minerals from that, from which you can really already get a very good, much better idea on the potential of this kimberlite. Would it carry diamonds or not? And I think Herman will talk a lot about that in the next couple of hours. You can probably get enough material to do your first microdiamond sample, and Hilda will discuss this in some detail, but that in addition to your mineral chemistry will give you a very good feel for, is this kimberlite interesting or is it not? And then using your geophysics, you add your size to it. So there you have, for relatively low cost, come to a point where you now have to decide, well, what am I going to, do I need to do more drilling to confirm the size, to do overburden thickness, to do some density tests, and more importantly, to map the kimberlite, because each kimberlite will have different facies, and that was discussed to quite a lot of degree yesterday. You need to know when you take your bulk samples, what facies are you sampling. So that then takes you to your evaluation stage. Do I bulk sample or do I walk away? And based on once you've done all this work and you've recorded it properly as per your SAMREC code, and you've done your sampling properly, you've done your laboratory techniques, you are in a good position to make a decision and take it to your board and ask either for more money, because bulk sampling will require a lot more money, or take a risk and walk to the next project. Quickly talk a bit about the geomorphology. It's very important in your target selection is to assess the terrain, the topography, the soils, and the drainage. It really dictates your results of your recce sample. And if you don't pick up your first grains in your recce sample, you tend to walk away from this area and may well be walking away from a kimberlite cluster. If you look at a geological time frame in terms of aggradation or even a degradation, about 90% of the time nothing really happens. And then you suddenly have a flash flood, you get some sand that comes in and it covers whatever was there before, or it cuts into whatever there was before. But that 90% of the time, there is actually a lot going on. This is when soils form. This is when you start weathering, chemically weathering your profiles. So your soil form process really depends on your climate. There will be lots of organisms active in that profile. It depends on your topography, on your water table, depends on your geology, but most importantly, it depends on time. And time, there is enough, millions of years. That,
you have 5 minutes time left, Mike.
Okay.
Time is, as you mentioned, important. Okay.
So if we look at calcretes, they developed certainly in the central part of our southern Africa. That's a photograph of a hard pen calcrete. It's made up of various stages of development. And it's very well described by Frank Nechtenberg. If you're interested, you should read that if you're working in Southern Africa, because it gives you a good insight how calcretes form. But more importantly, it has a very negative effect on your kimberlitic minerals. Here are two examples, one by Killam and one by Baumgartner in the Kalahari, where you see your indicator minerals decrease from your kimberlite, where there are lots of them, to almost nothing on surface if you have calcretes that have developed over these bodies. So bear that in mind. The effect of calcretes, they trap your minerals, they alter the surface features of your minerals, they break them down into very small grains that you normally wouldn't screen for, and they just completely destroy minerals in some cases in the low pH environment. The use of termites is therefore used in Botswana to some extent, and I'll discuss this a bit more tomorrow, so I'm not going to go into detail, but there are various publications on that. And that leads you to the group 2s, which don't produce ilmenites, and there are group 1s that also don't produce ilmenites. They occur generally outside of the Kalahari Basin. And so far, there's only 1 or 2 kimberlites in the basin that have been found to be group 2 and ilmenite poor. So it's a problem. And this is an example. That's the KX36 found in central Kalahari. There's results of group 1s, but this is a group 2, has very few indicators on surface, very difficult to find. Now, quickly diverting to the northern DRC, where you have massive lateritic profiles, and the main indicators in this area was actually diamonds, because the grains go through a lateritic profile that is very similar to your calcrete profile. It matures and it etches your grains, and this is what non-kimberlitic garnets look like. Look at the etching on these grains. You put that through a screen and it'll completely break and destroy these grains. So you end up with nothing. So again, something to think about in the future. We'll have to look at looking deeper, looking undercover, and those are going to be challenges for the new generation to think about. In terms of kimberlites, this is an interesting slide where you have years of discovery of kimberlites in Russia. The first kimberlites were exposed. The second generation of kimberlites were covered with shallow cover, and the more recent kimberlite discoveries in Russia are either covered with sediments or with basals. And it's a real interesting challenge. So geophysics is going to play a major role in your future exploration, and not just geophysics as it is, but the integration of different technologies. So the answer is, are we still going to find kimberlites? I believe, yes, there are diamond-bearing kimberlites still out there. The increase in the number of diamond-bearing intrusions with increasing age is more a function of burial rather than erosion. So we have to look undercover. Target selection is king. Have a look for sedimentary cover areas. Think about that carefully. And also how we take samples. Do we go smaller fractions? Do we have improved DMS recovery processes? And do we have areas with ilmenite poor kimberlites? And then the emphasis would be on sensitive geophysical techniques and the integration thereof. But never stop trying. I'm just listing a few people here as my last slide that were instrumental in finding big deposits. There's one common trend in these people. They have tenacity and they're optimists. And that's what you have to be if you want to get into the exploration side. You have to be both and have a drive for it and a love for it. Thank you.
Any questions for Dr. Mike?
Okay, thank you. I just wanted to ask, I believe you said in the 90s a large number of diamondiferous kimberlites were found. If you look at the huge increase in diamonds discovered, I know normally there's a decrease in the price after that. Why do you think there was a boom in the early 2000s price-wise after that?
Sorry, why was there a boom after the 1990s, after the discoveries of all these kimberlites?
Yes.
Well, I think there obviously a lot of companies that were mining diamonds at the time were involved in very aggressive marketing programs and which were very successful actually to able to market all these diamonds that are coming onto the market. And that's still something that's, I guess, going on at the moment. I remember being in De Beers that our marketing budget was much bigger than our exploration budget. So people have really been very successful in marketing diamonds as a commodity for love and for eternity, etc.
Thank you very much.
John, you may want to comment on that.
No, you're absolutely right, Mike. I mean, my question was going to be, you know, where do we have good skills and teachers in, you know, the whole thing that you've just mentioned of geomorphology, weathering profiles, you know, formation of calcretes. You know, there's a whole field out there. I mean, we have some experts like Greg Botha, but strikes me as it's, you know, it's one of these very broad but very important spheres of geology that we don't do enough work on.
Yeah, I think so, John. I mean, we had Tim Partridge and Rodney Maude and those people driving geomorphology as an important aspect. And geomorphology has moved on. It's become quite scientific these days in terms of appetite fission tract dating and cosmogenic dating and what have you. But it's still a very important part in exploration, and not just for diamonds, but for all sorts of other commodities, in understanding your media that you're sampling, your geochemical sampling. What does it mean, and how does it affect your results? And I can't think of where that's really been taught these days, but a lot of it is sitting in individual consultants that one has to perhaps at times call on to explain some of these processes.
Yeah, Mike, you know, is there a book or some kind of course that people can actually, you know, go out there in the field and show young budding exploration geologists just how to decide? Like you said, you gave some good examples of how to sample, where to sample, but that knowledge needs to be passed on. It needs to be decided. Is there somebody that can come from afar and actually show? Because you say once you pick one method, then you must stick to it.
Yeah.
And how do you make sure you sort of end up with a correct method of sampling? And how do you check these guys that are lazy, for instance? Do you have checks and balances back in the laboratory that shows that the guy's not just sitting under a tree and sampling around that type of stuff and then faking the results, you know, to get the results back in there, and the experienced guy to come and tell them how to do it?
I think, Annie, we were lucky to be at the University of De Beers at the time. We had people like Alex van Zyl, and it was trial and error. I mean, Gavin Lamont in Botswana, and I'll talk a bit about that tomorrow. He discovered that concentrating samples was better doing it with screen samples than using a gold pan, and that took years actually for him to figure this out. And also the scoop sampling method was developed actually in Zambia by Anglo while they were sampling for base metals. A lot of these techniques was by trial and error. People were experimenting and looking what was better than other methods. And you can't. I don't think you can write a book about it. Well, you could write several books about it. But every area is different. Every area has a different drainage pattern, has a different soil development, and you really have to use your experience and your best knowledge that you have to decide what your interval is going to be, and do some test sampling. That's very important. Orientation sampling is very important to give you the confidence that you're taking the right decisions of how to take a sample.
Yeah. Mike Juan du Plessis wants to know, says, excellent talk. How useful is manganese as an indicator for alluvial diamond deposits? Says he knows that it's associated with diamonds in the Northwest Province, but how does it correlate to other alluvial deposits like you found in the southern DRC?
I think it's interesting that a lot of the alluvials in the Northwest have associated manganese, particularly as little nodules and concretions and whatever. But there's no relationship, unfortunately. I mean, the manganese relates to the dolomites over which they form. And in some areas there are diamonds with it, and other areas they're not. So I don't think there is any relationship that one can use to say, well, there are manganese here, so there's going to be diamonds here. And I don't think that's going to be going to be possible. I don't think there's a relationship, unfortunately.
Okay. And secondly, wants to know if a deep erosional pothole found in a stream with a solid rock bottom mass could also act as a type of trap for diamond concentration?
Yeah, it's an interesting point, actually, because you'll see that people like Jürgen Jacobs done some work on the potholes on the Lower Orange. And in some potholes, you will get no diamonds at all, or no indicators at all. It's just been flushed out and filled with sand. And you may have to look just beyond the potholes. But in general, one would look at potholes, certainly for the trap of heavy minerals, but it's not always as straightforward as it seems.
Yeah, and maybe
Okay,
just the last
sorry.
comment there for Mike. I mean, Mike, you've been very good at it, and maybe it was, or I think it was something that we in De Beers back then were a bit remiss about, is using, you know, local expertise. For example, if you went to Brazil or Canada in a glacial terrain, you know, you really also need to go and look, you know, go and talk to the people who know, you know, in the case of Canada, obviously glaciology, and in the case of Brazil, it would have been that, you know, those deep weathering profiles again.
Yeah, there are good people out here. So as I mentioned, Frank Netterberg has done a lot of work on calcretes, and John de Villiers in Natal that was great on soils. But there are new people on the block that, and you need to talk to those people. You need to understand these processes are very important, and those people have a wealth of information, and they're generally quite happy to share that.
Yeah, and then Yamkela Makupola says, Mike, where do you get all of those books that you showed us at the beginning?
You get, well, a lot of them I got through Amazon. But the book on diamond prospecting by De Beers is unfortunately now out of print, and we're trying to convince the GSSA that we need some money to put a second edition out, because there's been a lot of interest in it, and it's just a very interesting book how people went about in the fields taking decisions, how to live, how to draw their maps. And how to take your samples, and it's a very interesting book to read from that point of view. So hopefully we'll get some funding to perhaps do a second run.
But
Thank
just
you
to
very,
answer,
very much, Mike.
Yeah, to answer Yamkela, sorry, Henny, I mean, at the end of the course, we can also put together a list of references. I mean, we have sent some papers to the students, but it's a good point. We'll put together a list and, you know, some suggestions of where you can possibly find those books as well, particularly the ones that are, you know, older.
Okay, the first session this afternoon is presented by Mike de Wit from the University of Stellenbosch. Mike's a long-term colleague of mine, obviously from our De Beers days. I think he was probably given an introduction yesterday for his presentation at that time. So I'll just allow Mike to commence his presentation. Thanks, Mike.
Okay. Thank you very much, Bill, for the introduction. And I'm going to talk about Botswana in a delayed session that was supposed to have happened 2 days ago. So maybe it's a bit out of sequence, but nevertheless, I want to give a little presentation about the Botswana prospecting history. And it was really a presentation I gave at the Kimberlite conference in Gaborone a couple of years ago. Just in terms of where Botswana is, and there's a map of Botswana with the main kimberlite fields, and also showing the main mines that were discovered over the years. Orapa and Letlhakane and Korowe in the north, Zwaneng in the south, and then Gagu and Lorala, where attempts were made to mine these deposits, but they are dormant and at care and maintenance at the moment. Just for your own interest, globally there are about 7,000 kimberlites in the order of. There are about 700 of those that have diamonds in them of sorts. And only 70 of those have been mined or are mined. So that's only really 1% of the kimberlites found. And out of those, there are only 7 tier 1, which are really world-class mines that we have globally. So that's 0.1% of the total diamonds discovered or kimberlites discovered globally. Now in Botswana, there are nearly 400 kimberlites. There are 6 operating mines. 2 have closed, 2 are on feasibility, but it also contains 2 of those tier 1 deposits. So it is a very important player in the global sense. At this point in time, Botswana has produced well over 800 million carats of the global amount of around 5.6 billion carats globally estimated to have been produced. So again, it just emphasizes that it's well overtaken South Africa in terms of historical production, and it is a very important player. Just a few points for your information in terms of how we express kimberlites in terms of surface areas. We use hectares, and you may have heard that term several times. A hectare is 110,000 square meters. So one expresses this in terms of surface areas of various kimberlites. There's the Orapa kimberlite in Botswana, well over 100 hectares, a very big kimberlite, almost as big as the biggest in Africa, the Madui kimberlite. And then there's the Zhuaneng kimberlite with almost 37 hectares, also a very big kimberlite. Just to recap for the case of your information, a carat is 0.2 of a gram. It has a hardness of a SG of 2.52 and a hardness of 10. Grades we often talk about in many of the talks is expressed in carats per 100 ton. And values are often talked about is expressed in dollars per carat. That's just to add some background to it. In terms of Botswana and Bechuanaland, as it was called in the past, I've sort of subdivided it in 3 stages, and I'm not going to hamper a lot on the first 2 stages, but it's interesting that there were, like many parts in Africa, certainly people that were mining and digging out stones for various tools, and that these tools are recognized as the earlier, middle, and late Stone Age periods. Minerals were used for pigments and rock paintings, decorative purposes, and also early mining in Botswana has been recognized both in terms of copper, gold, and iron. Then in terms of historical part of Botswana, and that really started in 1860s when gold was rediscovered in the Francistown area, and that led to various prospecting stages for diamonds, and we'll go over that. And then in 1959 is really when the modern diamond exploration program started in Botswana, with first diamonds being found by Consolidated African Selection Trust, and followed by De Beers, Falconbridge, and various other major companies. So if we just go back to the prehistoric times, it's the Magadi Pans is a very interesting place in terms of that. You can recognize, you can even see that on Google Earth, you can recognize various strand lines along the pans, which illustrate the level of water that was in those pans, and on the edges and along the edges of these strand lines, one can find artifacts where people were picking up stones and transferring these into tools for use as varied purposes. And it's interesting that some of the early Stone Age artifacts have been found near Orapa, but also some artifacts have been picked up at the base of the Kalahari on top of some of the kimberlites. So that gives you a sense of the depositional period of the Kalahari sands that must have come in after the early Stone Age. In terms of using minerals for pigmentation and so on, there are some mines at Tsodilo Hills in the northwest of Botswana, one of the bigger hills in the country. There's a little photograph of the old mining sites, and there are some very nice rock paintings on those rocks at Tsodilo. But also there are some prehistoric copper mines in the Dukwa, in the sort of eastern part of Botswana, and these are still being examined, particularly people like, there are some people in Francistan that are investigating and looking at how these various minerals were mined between 800 AD and 1200 AD. However, if we go back to, if we start looking at the proper historic mining, first of all, in 1866, gold was rediscovered in the Tati area, and there was a lot of activity there till about the 1970s, when diamonds were found in Kimberley, and a lot of these early discoverers moved to Kimberley rather. In 1885, southern Bechuanaland became a British protectorate, and 5 years later, they included the northern part of Botswana, separated by the 22 degrees degree line. So it was in two stages that Bechuanaland became a protectorate from the British. In 1895, the three main chiefs of the three main chief areas were concerned about the influence of Cecil John Rhodes, particularly after he started annexing the Rhodesians, and they were concerned about Botswana's independence, and they went to England to plead for Bechuanaland to remain a protectorate and not to be transferred to Cecil John Rhodes' company, the British South African Company, and that was successfully achieved. So in 1896, after that event, the first expedition of some real prospecting took place in northeast Botswana. This was a company called the British West Charter Limited. And if you go back to the directors' documents and so on, these were many of those directors of that company were actually personal friends of Cecil John Rhodes. So it was quite clear of how he wanted to establish the presence of diamonds and gold in Botswana. Now, so he sent an expedition to Ngami Land in the northwestern part of Botswana, a very difficult place to get to. And this was led by a German by the name of Siegfried Passarge. They spent 3 years exploring this part of Botswana. He wrote a very extensive document on that, produced also the first geological maps of that part of the world, didn't find any kimberlites, covered areas where quite a long time later, 1979 and 2009, the first kimberlites were in fact discovered. Interesting, he wrote this book. It's available. It's about 800 pages. It's all in German. So if you're quite keen to read that, it's quite a challenge. But he was a doctor by training, and he ended up as a professor in geography. He was a naturalist, and he had a very great interest in things like termites, for instance. And there's some fantastic drawings of how termites operated in that part of the world, and we'll get to the importance of that a little later. There were no diamonds and gold was found, but he was obviously not permitted at the time to release any results. Some years later, after that expedition, Alex de Toy came into Botswana. He was working for first for the Geological Commission when he came to South Africa, but then for the irrigation department as a hydrogeologist. And they wanted to know if they could some way dam off the rivers in the Magaligaan area to fill this area with water and change the climate for agricultural purposes. So Alex de Toy spent some years there, and he wrote a very interesting paper called The Crustal Movements as a Factor of Geographical Evolution of South Africa, where he identified these what he called upwarps in the crust in several areas in Southern Africa. And again, we'll get to that as in a little later of the importance of that. He, after his spell as a hydrogeologist, he became chief consulting geologist for De Beers, where he retired. And he, in fact, prospected parts of Botswana on behalf of De Beers. Just a little background on the Bangmawati Reserve, where the gold and the copper was discovered. The Khama III, who was chief of the reserve, signed an agreement with a company, North Goldfields Exploration. But Cecil John Rhodes took that company over in 1893, obviously keen to get into Botswana. But Khama's the third successor, Sekedi, was not keen on that initial agreement, and they had a long renegotiations to revisit this agreement, and eventually they came to take an agreement, and Anglo and De Beers entered Botswana as the Victoria Prospecting Company Limited. And 2 years later, Anglo abandoned it, but Alex de Toy, who believed that there were certainly kimberlites in Botswana, felt that it was worth carrying on, because although they hadn't found any interesting results, they did identify several areas with substantial gravel deposits. And he convinced De Beers to do some testing of some of those gravels, and found the first diamonds, authentic diamonds in Botswana, in the south eastern corner of that country. However, De Beers then after that pulled out, and it was many years later that they came back. Just a bit of background on Sekedi. He was the second son of Khama III, and therefore he was not eligible to become his successor. But the son of the oldest Khama's son, Seretse, was only 4 when his father died, and he was too young to take over from Khama III. So Sekedi became the guardian until much later, after Seretse Khama went to Oxford in the UK, married Ruth, which caused an interesting political aspect of Botswana, entered politics, but became the first president at independence in 1966. However, Sekedi did feel that development should take place in Botswana, and he signed an agreement with the Rhodesian Selection Trust in 1959. He didn't want to sign any agreements with South African companies because of the politics. This African Selection Trust got the rights to prospect for copper, but he also got the rights to look for precious stones. They had been working in Sierra Leone for many years, and they came to do some bulk sampling in that eastern part here of Botswana, and in fact they found the first diamonds in a stream sampling program. This is an old map of their reports that they submitted to the government, and you can see the position and the sizes of the diamonds that they recovered from their stream sampling. They didn't work further west, because they came across, it was the start of the Kalahari Basin, and they felt they weren't equipped to handle the sand and sample the sand more to the west. And they also thought that there is some Dwaika in the Maklutsi. They thought that maybe these diamonds had come out of the Dwaika. So they dropped the ground and basically left the country. So the next person of importance of the discovery of kimberlites in Botswana was Gavin Lamont. He did his PhD in the Van Reinstorp area, and his external examiner was Alex de Toy. So he knew Alex to some extent. When he finished, Alex suggested that he should get experience in African countries. So he went to southern Rhodesia, and then he went to the Bechuana Protectorate and joined first the Geological Survey in 1949, but then joined the Anglo-American De Beers group in Botswana to start exploring again in Botswana. And one of the things that he found is that the termites may have had a major impact in bringing material from below the Kalahari sands to the surface. And he was quite keen to sample these. There is a very interesting book, and it's first published in 1925 by Eugene Moret. It's very interesting to read. And it describes how ants develop and how they live underground and move massive amount of material to the surface. So Gavin felt that bioturbation by termites over hundreds of thousands of years has brought to the surface from kimberlite pipes the garnets and ilmenites that we are able to successfully use in our soil sampling program. So that was his take on the termites. It's worth looking at that because it's applied in many other countries, in Australia as well, in geochemical sampling, where they use termite activities. The way that Gavin Lamont then started prospecting in Botswana, he had large teams, and they walked the ground along cut lines that they made, north-south cut lines, and then they walked the ground from the cut lines 5 miles in, a mile across, and 5 miles out. And a sampling team would consist of a team leader, a wheel pusher who would measure the distance with his clinometer on his wheel. You had 2 samplers on either side of the team leader, and then a whole bunch of porters that would carry the samples back and forth from the baseline. There's a photograph of a typical sampling team. They would then scoop every 12 to 15 paces, a scoop. They would put it through a sample splitter, and every 0.2 of a mile, the team leader would blow a police whistle, and 2 bags were filled in 1 bag, and every 1 point, so that would be 1 sample, and every 1.2 miles were 6 samples that would have to be carried back while they're going on the traverse back to the baseline, where a vehicle would be waiting to load it up. So that was quite a military style operation that worked like clockwise. And that's just a photograph of the guy taking a scoop sample, dumps it into the sample splitter. And there's a photograph of the guy with the wheel. He's got a compass in his hand as well. And he's also carrying 2 of the samples. So multitasking, if you like. In addition to the sampling that Lamont introduced, he also looked at the concentrating methods, and that took a while for him to realize that panning for indicator minerals was not very efficient, and he decided to start screening the samples and hand gravitating these in a drum, as we discussed yesterday. In that way, one of the first things that the BS did is to resample the area that the Selection Trust had sampled, and they found 2 diamonds in approximately the same place as Selection Trust. But the other thing that they found was garnets, ilmenites, and even CDs. So that was a step forward in terms of recognizing the possibility of finding perhaps a primary source. Lamont was very keen on this area, but the licenses had been, some of the licenses had been expired, so they were then working in other areas. But going back, the reason why Lamont was interested in this area was there is the rough position of the diamonds that were found in the Maklutsi River, and that's the rough position of the Rapa province, and it's separated by this Kalahari-Rhodesia axis of Alex Satori. And the theory was that this up axis would have dissected the drainage that originally would have come across this axis, and the upwarp of this axis would have cut this river system, and therefore the source of the diamonds of the upper Maklutsi River would have to be on the other side of the upwarp. That was certainly a strong case that the Toy made. Before getting to that, the bears were busy in the southern part. They found their first so-called kimberlites. They were not true kimberlites, but nevertheless, they found two pipes that were very interesting, and it gave them the confidence to that the technique that they were applying in terms of screening and loam sampling, that it worked. And at the same time, there was a person called Chris Jennings, who started working at the Geological Survey 2 years after Gavin Lamont left. He was mainly into groundwater and made extensive use of geophysics. In fact, he did his PhD in Botswana on the hydrogeology. And his interest really was geophysics. And he also left the survey and in 1971 and joined a company called Falconbridge. Now, before he left the survey, he and Lamont were fairly close. I mean, it was a small geological community, so everybody knew each other. And he invited Jennings to come and do some tests of geophysical surveys over the maturity bodies that they just discovered. And the conclusion that Jennings came with, he applied various techniques, seismics, electrics, and so on, is that magnetics was really one of the better tools to use. And in 1968, after the discovery of AK1, in fact, Jennings came up to do some test lines over that kimberlite. So getting back to Lamont and the upwarp, there's a Google 3D image of that upwarp. De Beers had been in Botswana now more than 10 years, and they hadn't had much success, so they were putting the pressure on. They gave Lamont another couple of months to do what he felt he had wanted to do in the first place, is to go to this area and do some very crude road sampling. They collected various large scoop samples. They camped at a little pan with a bit of water, and they found that 12 of those scoop samples were full of indicator minerals, garnets and ilmenites. So they then knew that they were onto something. And this was in July 1966. It was just before independence, September 1933. Botswana became independent, and the first president was Sir Cyril Sekama. He was a very wise diplomat. And one of the things that he did was to invite all the chieftains to a conference in which they decided that all the wealth of Botswana should not be part of, go to the chieftains, but should be part of the nation, irrespective of where it was found. Shortly after independence, De Beers managed to get their licenses, and they sent Manfred Marx there in 1976. And he, in fact, found the first kimberlite by doing some detailed sampling, digging a pit, BK1, in March the 1st, 1976. This was followed very shortly thereafter by BK2, and then the big one that he found in April 25th of the same year. This the team that recovered the first indicators of the first samples over AK1, which is the Orapa mine, and there's the mineral count, a microabundance of ilmenites, garnets, and CDs. In fact, Gavin Lamont still, I've got a letter from Gavin Lamont with the first indicators from Orapa stuck on it, which he gave me when I discussed the history with him in some detail. Now, there were some air photographs available of that area at the time, and it shows you very clearly the outline of AK1. There's AK1 on the photograph, but also some of the other kimberlites shown. There's hardly any cover here. There's some calcrete that developed over these bodies, and there's some dolerite dikes that stand out very nicely. But that was, it's a very nice photograph to show you that if you do go into these areas as discussed yesterday, do have a look at air photographs of places. You'll be surprised to see what you can find out of that. It was interesting because this particular feature was used by the by SA Airways and their flights from Johannesburg to London as a beacon on their trajectory. And the initial evaluation of Orapa was done with a rotary pen that came from Kimberley. It was a 6-foot pen, quite a small one actually, and small pits were dug, 9 by 9 foot, 20 foot deep. But this was, when the results started coming in, this was fairly quickly overtaken with the introduction of a DMS plant and much deeper and well organized pits. The first diamonds that came out were quickly identified and obviously added to the excitement of this discovery. Airborne surveys were flown, and I showed you this thing, yeah, these photographs yesterday. That's a very early stage airborne survey, but also an input electromagnetic system, which was attached. There you can see the wiring to this Catalino aircraft. That's the status of the discovery of the Orapa kimberlites as we see it. There's about 85 kimberlites. It's probably close to 90 now. Lots of them are quite small. A lot of them have very few are no diamonds. There are only there are 4 mines that have come out of this. That's AK1 up here. Then there's the Damsha, which are 2 kimberlites, BK9 and BK12 here. Letlakani mine, 2 kimberlites, and then the Koroa kimberlite. But people are still looking at BK11, BK16, and several others. So it's still a work in progress in many respects, and people are still exploring in this part of the world, hoping to find undiscovered kimberlites. That's what the open pit looks like 2 or 3 years ago. It's 118 hectares in size. It was commissioned in 1971 after being found in 1967, a really very fast move from exploration into mining. And it's produced well over 400 million carats, an enormous contributor to the global diamond pool. It's got a very interesting crater with lots of interesting fossils in them, and it tells us quite a bit about the paleo environment at the discovery at about 95, at the emplacement of 95 million years of this body. It was officially opened by Sir Soretsi Kama and Harry Oppenheimer, and it's interesting that quite soon they realized that they have to form they formed a joint venture company between government and Botswana, a 50-50 joint venture, which was obviously very advantageous for the state. But the Beers, I think, did a marvelous coup there and set themselves well up in Botswana. In the meantime, sampling was going on in other parts of the world, and sampling was going on in the Zhuaneng area. This area had been sampled in '62, but no grains at that time been recovered, and it was really because the sampling technique was still on the old side, the old way of doing things, and also the concentrating was done by panning and not by screening. So the first reconnaissance results, positive results, came out in '69. Then detailed sampling was done, and this produced various ilmenite anomalies over these bodies. And drilling started in '71 on DK1 and DK2, but failed to intersect any kimberlite. And it's very interesting, as they were using a Vol tractor mounted drill that was used in Orapa. And Orapa, there is no cover. The limit of depth of this particular drill was 50 meters. And so the cover in that area is 50 meters. So the initial holes were drilled without success. But after rethinking and putting a bit more effort in it, the first kimberlite was in fact drilled in 1972 under supervision of Stuart Verco with Norman Locke on the team. And this followed fairly quickly with the discovery of several other kimberlites, and by 1979, 11 kimberlites had been discovered. The next problem really is now to evaluate the Zhuaneng kimberlite. It was under 50 meters of cover. Drilling started using a jumper drill. This had a very large bit, almost half a meter in diameter. But because of the low penetration, the penetration rate was started at about 5 meters per shift, but soon, once kimberlite was intersected, harder kimberlite was intersected, reduced to about a meter per shift, which was surely not enough, was surely far too slow to cover all these holes and get a decent sample for the first evaluation project. In addition, they also found that a lot of the diamonds that came out of the holes using this technology were broken. So this technology was later replaced by rotary percussion drilling and proved to be a much more effective tool. And Zhuaneng came into production in 1982. That's a bit of an older slide of Zhuaneng. It's a massive pit of 3 adjacent kimberlites. It was commissioned in 1982 and so far has produced almost 400 million carats. So between Orapa and Zhuaneng, Botswana produced well over 800 million carats, with Zhuaneng and Orapa each with about 400 million carats each. It's presently going down to, the pit is planned to go down to 625 meters. It's got a high grade and it's really one of the richest resources of any commodity that one can think of in terms of revenue per ton. When the cut is finished, you can almost fit 2 Eiffel Towers into the open pit, a mega pit, so to speak. There is obviously huge cost involved, and at the time the planning was to spend $3 billion US to get this pit done because of the overburden stripping. But it takes the mine through to well over 2028. And Zhuaneng has produced some fabulous diamonds. One doesn't hear a lot about it, unfortunately. More recently, it has recovered a massive diamond. So it certainly has produced some very interesting and very valuable stones. This is the latest large stones of over 1,000 carat that came out last year. Gives you some idea what it looks like. Probably it looks a bit like a type 2. I'm actually not sure if we know that yet. But certainly they do occur at Zhuaneng at quite a rate. During this time, there was a publication in Economic Geology by the Geological Survey that on gold, base metal and diamonds in Botswana, but there was a map in there in which they showed what areas De Beers had covered and what areas De Beers had proved to be positive. Now, De Beers hadn't been able to get to all these areas where they had positive results. And so this information was taken over by Falconbridge, who then decided to look at areas where De Beers hadn't got to yet and where positive results had come out in the early days. And they focused a lot of their work in the Tsabong and Kokong area, and also started working in the Central Kalahari Game Reserve. Their approach was very different. They decided not to necessarily use the walking military approach of Gavin Lamont, but they used helicopter support sampling, and also their drilling was very different. They used a technique that Chris Jennings knew existed in Canada, and was able to drill these targets that they were getting also from their airborne geophysics. Remember, Chris Jennings was deep thick into geophysics, and he believed very much on airborne geophysics. So they flew big areas, and they found a lot of kimberlites between. In 4 years that they were in Botswana, they discovered 62 kimberlites. So their approach was good, but they weren't successful in finding anything of economic interest, except in the Central Kalahari Game Reserve, where this is a photograph of Andy Lamont and Andy Murray in his early days. He was doing soil sampling by helicopter in the Kalahari Game Reserve. They covered this area fairly quickly, and were able to find various anomalies, but one of which was Hopi, what was called Hopi 25. It's now called Chachu, and certainly a kimberlite with diamonds in it. The problem with that kimberlite is that it was sitting under 80 meters of Kalahari cover, and evaluation was tough. It's a 10 hectare body, and it's been sitting on the shelf for a long time before Gem Diamonds took it over, who had a go at it and put in a decline, which we'll come to in a minute. De Beers then started soil sampling. There's your soil sampling grids in the east of the country where there was no cover, and they found two small clusters of kimberlites. Interesting enough, both of very different ages, one of 1300 and one of 500 million years, in the close to the Limpopo River. One cluster of which contained diamonds, and the other which was barren. These were very small in size, 0.2 to 2 hectares, but had a reasonable grade. But their diamond quality was not what would have made it economic. So those projects were shelved for the moment. And in 2003, a lot of interest came back to Orapa, and people started re-looking at some of the kimberlites that De Beers had found. This was at the time called AK6. It was reported by De Beers as a 3 hectare body and had a grade of 3.5 carats per 100 ton. It was revisited by African Diamonds, and it certainly came out that this kimberlite was actually much bigger and had a much better grade. It was certainly subsequently taken over by Lucara Diamonds and produced some fabulous diamonds, which Ray Ferrara spoke about early in the week. Certainly some of these very large, very special stones have come out of that deposit. In fact, if you look at some of the results since 2012, when they started mining it, over 200 diamonds of $1 million each have come out of that deposit. It just shows you the value of that particular kimberlite and what sort of stones it has produced. It's just incredible. I don't think there's anything like it on this earth. It produced 3 diamonds over 1,000 carats. It produced 25 diamonds over 300 carats. It's just an incredible producer of big stones. And having recognized this, Lucara started changing their plant structure to avoid any major breakages of these big diamonds. They put in autogenous milling. They put in XRT, X-ray transmission technology to try and detect diamonds before it enters the crushing circuit, to try and recover diamonds that would have otherwise probably have been broken. Going back to the Chacho, or the Hopi deposit that was found by Falconbridge, eventually in 2012, Gem Diamonds decided to try and give it a go. They put a decline in under the Kalahari into the kimberlite. They acquired this from De Beers after De Beers had acquired it from Falconbridge. It was opened in 2014, but it was put on care and maintenance in 2017. Incredibly difficult mining conditions. The instability of the overburden made things difficult. There were water problems. So it's an underground mine, but certainly not one that has faced the test of times at this stage. Just to then summarize in terms of where the discoveries were made and sort of what time and at what interval, there was certainly the 60s and the 70s up to this point in time were big periods for De Beers. This time in the late 70s, early 80s is the period of Falconbridge. and then De Beers finding additional discoveries. But by sort of early 2000s, the sort of discovery rates dropped dramatically, and at the moment, the amount of discoveries from what's coming in from Botswana are quite small. It's also interesting to see that all these early discoveries were made by sampling using ilmenites, right up to almost to 2007, when people start looking at garnet anomalies and using geophysics. So it shows you the importance of ilmenites, and it's certainly finding all the group 2, the group 1 kimberlites. Remember, group 2 kimberlites don't contain any ilmenites, and you get also group 1 kimberlites that haven't got any ilmenites. So I think there's still quite a lot of potential of expanding on the exploration and looking at some of those garnet, early garnet recoveries. Interesting, this period is really where all the mines were found, the Urapa, the Zhuaneng, and after that, several kimberlites, but not something that you can get your teeth in. In terms of production, what Botswana has produced, Botswana sitting now at about 850 million carats, and it shows you the amount of carats with time. And when different kimberlites came into production, Urapa, Letlhakane, Zhuaneng, there was a big jump at Zhuaneng, big push on the kimberlites, new plants, etc. And if you look at the GDP of Botswana at the time of discovery, it was $84. In 2018, I'm afraid I haven't updated this, but it was well 100 times higher than it was in those days. So it has done an enormous amount for Botswana as a country, the development of country, the tar roads, the clinics, the universities, the schools. And a lot of that had to do with the vision that both Khama and Harry Oppenheimer had in terms of forming a 50-50 joint venture, making that a state company, and a partly state company, and channeling all those funds back into the country. So my view of Botswana is it'll remain a major player in producing diamonds for decades to come. But to me, it's also still a very attractive country for exploration. And I think this is something that you're going to have to think about. It's a country that's got great cover, not only for Kalahari, but also for Karoo. We have definitely got pre-Karoo kimberlites in Botswana in the east. So there's no reason why there shouldn't be more towards the west. The Kalahari cover makes exploration quite difficult. So we have to really think about carefully how you would tackle the future of Botswana. But it's politically stable, and B, it's got a good infrastructure, and most importantly, it's geologically a very attractive target still for diamond exploration.
I've just got maybe just one comment. I mean, we've looked a lot at the Toy's uplift axes. I've wondered, that maybe they're not recent uplift axes. They're more like fossil watersheds, because they really separate areas where Karoo is on one side and not on the other side. So perhaps we've had gradual downward erosion of the old landscapes, and then you expose those watersheds, which is why that one around Maklutsi is now being exposed, and it's been the old Okavango drainage has been now cut off from the Limpopo drainage. Yeah,
Bill, I can't agree more with you. Actually, I've always had a problem with these upwarps, even in South Africa. Going through the Lichtenberg area and so on. But I mean, it's just that it's interesting that the Toy's theory was tested by Lamont, and I don't want to go into the technical side of things, but It's an interesting theory, and it did lead, whether it's a recent upwarp or whether it's an old drainage divide, it did lead them to the discovery. So it's an interesting story from that point of view. But I do agree. I think a lot of these features that we see are in fact all pre-Karoo already. You can see how the Dwyker sort of avoids some of those those axes. So I tend to agree that I think these things are old things. They may have had a bit of rejuvenation here and there, but I think the origin lies well back in geological time.
Yeah, some of these features may actually be, as I said the other day, pre-Karooan age.
Yeah, exactly.
You know, if you look at the Michalisburg, you know, sort of trend there, because that's the east-west trending one that the toy has. You know, that could have existed in pre-Waterberg times.
Yeah, yeah. I think that some of these things are very old. Yeah.
Yeah. Anyway, the floor is open for questions. Tanya, have you seen the chat? I haven't seen anything.
There are a couple of questions in the chat from Ketso, who asks, Mike, with little erosion on the Orapa pipes, where exactly do you think the diamonds found in the Mitlutsi River came from?
Well, it's a very good question, actually, and it's exactly what we're talking about now, because the present day erosion of the little erosion that Orapa has experienced, the present day erosion and tail of those diamonds is actually going to the northwest into the Makharihari pans. And there are some gravels that De Beers have looked at, they're called the airborne pan gravels, and they are definitely mineralized. So whether the diamonds that are found in the Mitlutsi are actually from Orapa is a very good question. There may not be. Maybe, and I have thought about that a lot, and have looked at that western part of Orapa quite carefully when I was still working with Todilo. So I think there's still potential for that, and therefore we shouldn't exclude that idea at all. I think that's a very good point, and maybe that whole axis and the discovery of Orapa was just coincidental, as we just discussed early on.
His second question, and there are three of them. The second one is, where is the next frontier in diamond exploration in Botswana?
Well, you got to pay me to give you that answer.
And what's the potential of alluvials in the Mitlutsi River and other ancient rivers in central Botswana?
Mike, you need to add in it's upfront money, not after the event.
Yeah, Bill, and it's dollars, not rands.
I will take pulas. The first question is, where is the next frontier? I still think that you have to look at the Archean. So you have to put up your Archean craton on that. That would then be quite, it would sort of take half the country away, the western and northern part. But
sorry, Tanya, will you let Herman in? Sorry.
And then that area, I think west of Orapa deserves a lot more attention, west and south of Orapa. So that's an area that I was always quite keen on. In terms of the Mitlutsi being a alluvial, I don't think there's potential for that. Toy tested that with his team from Kimberley. They did bulk sampling of the Mitlutsi, actually didn't find anything in that. And the diamonds really that occur to some extent on the alluvials would be from Orapa. It is very interesting to speculate where diamonds would have gone from the Zhuaneng pipe, and that's something that a lot of people would like to get some answers on. But the Malopo River has produced some diamonds, and there certainly are some terraces that people have tested towards the middle pit side, a bit more to the west on the Malopo. But as I've shown you, the Toy tested some of the gravels south of Labatsi and did find some diamonds. And these are probably linked more to the Lichtenberg side and the Mafeking side of things.
This next part of that question was the potential of alluvials Mtlutsi River and other ancient rivers in central Botswana. You really touched on it as you went through the discussion. And John Blaine just commenting, how about the Orapa discovery being serendipitous? Lamont and Gibson just doing the right thing in the wrong place at the right time. Well, they were certainly doing the right thing. I think the rationale was probably, you know, my view is the rationale was correct. You know, just the only thing might be, as we discussed now, the age of those uplifts.
Yeah.
Like the other thing is, of course, that Okavango drainage, you know, goes all the way back up into Botswana, so into Angola. So Angola could have been a source of some of those diamonds.
Yeah.
And then Orapa becomes serendipitous in terms of Mtlutsi diamonds, and even Sita, because you have those diamonds in the alluvials at Sita as well, which you can explain as, you know, people can say, well, they've must have come from Venetia, but those alluvials sit on top of the Karoo.
Yeah.
If they are, you know, they would have to have been very recently deposited when Venetia was first exposed from, you know, by the stripping of the Karoo.
Yeah. Yeah, I think there's lots of this Mtlutsi is certainly not sorted out into. There are still possibilities, I think, there, and I favor almost a more proximal source. But that's just my personal preference. We don't see any diamonds along the Okavango, actually, at least reported diamonds along the Okavango up to until we get to Orapa. But yeah, so I think that Botswana is still a very attractive country to work, and I think we're still in for some surprises there.
Okay, greetings everyone. Our next presentation is by Debbie Bone and John Ward. They will be talking about pink gems and purple hearts from the Cow Diamond Mine treasure trove in Lesotho. By way of background, Debbie holds a GIA Graduate Diamonds Diploma and a GIA Alumni Association membership, and is a highly experienced rough diamond valuation expert with lengthy experience in diamond tenders, marketing and sales. She joined the Makwa Diamonds in 2011 and is still with the company and a very key member of their diamond management, marketing and valuation team. John Ward holds a doctorate in geology from the now University of KZN and has worked in about 26 countries, 20 of them in Africa, mainly on alluvial and kimberlite diamond projects, ranging from greenfield exploration through to large-scale mine production operations. So over to both of you, and we look forward to your presentation.
Yeah, thanks, John, and thank you very much for inviting us. We're very excited to be here and look forward to sharing with you all about our pinks and purple hearts of the Cow Mine. Okay, so the whole talk is about the Cow Diamond Mine setting, its background, our pinks and our type 2s, the purples and the type 1s, and the revenue contribution and what's going to be happening in the future. Okay, so at the beginning of the summer school, Paul Simensky pointed out that why are pinks so rare? Well, they're pretty rare because there's hardly any mine out there that can recover the quality and the quantity of pinks that Argyle has done in the past. And the Cow Mine is now proving itself as being one of the rivals to Argyle, although Argyle is no longer operational. They are very expensive generally, and most type 2s pinks are type 2s, but throughout all diamonds, about only 1 or 2% of diamonds are type 2s in any case. But of that, the pinks usually command a plus 6 times more revenue than any other stone on the market at the moment. There's not very many mines out there that have a reliable source of pinks, and it's quite a good, it's quite recommended that if you can find 1 or 2 pinks in your mine, it will keep you going for a bit longer due to the value. Here you can see one of our classic, most highly rated stones, our Rose of Cow, 29.59 carats. It was recovered in 2018, and this particular stone got a revenue of over $200,000 a carat. Where do we find pinks globally? As I said earlier on, Argyle produced well over 90% of all pink diamonds in the world until November 2020, when the mine closed down. And the largest pink that they have recovered was a 12.76 carat. But not all the Argyle stones were of gem quality. But then the rest of the pinks come from throughout the world, from Russia, India, Indonesia, and Brazil, and in Africa that produces most of the remaining 10% of the pinks. And the record recovered so far was 132 carat stone. John, where was that stone recovered?
That was recovered from Botswana. And if you have a look at the map there, you can see the countries that have produced the pinks, with Tanzania, Botswana, RSA, South Africa, that is, Lesotho, and Angola and Guinea producing from kimberlites. Although Guinea, I must say, that they were recovered from alluvials on top of kimberlites there. What's interesting is that Namibia has also in the past produced a few pinks that have trickled down out of the interior of South Africa, and those are in the alluvials and a long, long way from home, whereas the other pinks have come really pretty much out of the kimberlites and proximal alluvials in Africa. But Africa certainly, as Debbie said, it's certainly the main contender for that remaining 10%. And with Argyle closing, it certainly puts some focus on where the records are from Africa. And that's what we're going to chat about today, because Lesotho, where Kara is situated, has some interesting results in the last years. So over to Debbie.
Okay, so this, you can see Lesotho down there in the bottom right-hand corner. That's where the Cow mine is situated. Okay, John, do you want to speak?
Right. Okay, yeah, so Cow mine's, it's right in the northeastern top of Lesotho, up in the Maluti Mountains. And it's part of the so-called Big Five kimberlites up there. These are Cretaceous age, Group 1 kimberlites. Letseng, Matai, Dikabong, and Lempani being the other 4, and Cow's the biggest at 19.8 hectares. It's operated now with in a JV, 75% Namakwa Diamonds through the operating daughter company, Storm Mountain Diamonds, and 25% of the government of Lesotho. So that's where it is, right up in the mountains. It's not as high, funnily enough, as the other 4 pipes. It's somewhat more eroded. We've lost about 750 odd meters off the top of Cow. It's gone down into the orange drainage system, and it was first discovered, and we put that in inverted commas because Cow was known to the local population as a source of ilmenite long before it was recognized as a source of diamonds. But essentially from 1955 on, Cow's had quite a bit of attention paid to it, but it was only about 10 years ago that it really came into commercial production. So a long history, but a long time coming into its own as a commercial mine. So this is just a view of the Maluti Mountains, looking southwards over the Cow pipe itself. The kimberlite pipe is outlined in black there, and there are 5 major kimberlite types that we've recognized. There are a few more, but we tend to rather aggregate than subdivide in terms of the commercial operation. And in emplacement order, we can see from the eastern side of the pipe, there's a K6 wedge over here. That was the first phase of kimberlite. It's a high grade, and it's only preserved in a wedge. It's not preserved inside the main pipe itself. The second phase of emplacement was what we call the LQ. The nomenclature here is, if you can use the word facies, domains, phases, whatever you like. We have stuck very simply to some some words here that reflect and preserve the history from Dave Rolfe in the early 1970s, and we've combined that there. So basically, K6 came first, followed by LQ, what was called Lower Quarry in the early days. And the most of the pipe is actually filled with the so-called fragmental kimberlite in Dave Rolfe's terminology. We just call it FK, and put a few of his subdivisions all together here. And then the final phase of emplacement is GK. Those are the commercial units, the economic units. There is another wedge, K12, which comes out here between LQ and FK, but this is not economic, it's a sub-economic unit. And you can see the plant is built on it, so we took risk back 10 years ago, and I think it's still justified not to follow that up. Down on the bottom left-hand side, you can see a Vulcan model of it. Data mine and Vulcan is what we have used in the past, and you can see there's the K12 in green coming out here, K6 in purple going off there to the east-southeast, and then LQ plastered on the side, with fragmental forming the pipe. And then the last phase of intrusion is this so-called GK. The original name was gritty kimberlite for that. Okay, the Cow itself, it's not exactly a high-grade mine. In fact, it's a low-grade mine. Most of the units are less than 8 carats per 100 ton. It's only the small K6 wedge that was high grade, between 15 and 25 CPHT. But what is interesting is that the gem quality is good, 65% in here, and this is consistent over 10 years worth of production. This hardly changes. And here gem at 10 and rejections at about 25% of the mine. If we have a look at the two photos, this is what it looked like in 2012, pretty much when commercial production commenced. The pipe had been fiddled with by a few operators before, dating back to 1957 in Jack Scott's days, when he took out 17,000 carats from this K6 wedge over here. But nobody had really tackled the rest of the pipe properly until Storm Mountain Diamonds got going in 2010 with the 2 years of preparation work, and then 2012 we went into commercial production. 10 years later, this is what the pit looks like. As you can see, it's a sizable pipe, and because of that, we actually have a bit of room to play in terms of strip ratios, and that helps with the marginal nature of the kimberlite itself. Plant is off to the one side of the pipe over there. So pretty much just over 10 years worth of, or 12 years worth of operation, 10 years of commercial, nearly 7 million stones, just about 2 million carats have come out, and out of 38 odd million tons. The average grade is just over 5 carats per 100 ton. That's a recovered grade, of course, at just about 0.3 carats a stone. So it's we've got a big history on the 2 million carats, and that's pretty useful for us in terms of where we're going to go forward today. So the initial work, the initial focus in Cow, this is a view looking north over the pipe just before the main production began in 2012. And you can see this little funny triangle on the eastern side here. This is the K6 wedge that most people had a crack at, leading up to 2012. So all the initial interest was in the 1.1 hectare high grade, and it was dominated by type 1 diamonds. And these are really commercial white octas, some light yellows and some fancy yellows, but mostly commercial white octas and dodecks. And this is where the resorption trend that is well recognized, and Farnes presented that earlier, where the range from the octa to dodeck was originally described by Keith Whitelock, who's been instrumental in getting the kimberlites in Lesotho up and running as commercial ventures from the late 1970s. So what we can see is that the dollar per carat in Cow, these commercial white stones in those early years, was twice of what was known in the rest. So it was fairly obvious that everybody was going to focus on this part of it, and it was really somewhat of an unknown area, the rest of the 18 odd hectares of Cow when we went in there. Right, so under Cow, so under the initial kickoff, obviously the focus was on looking after your paying back capital, etc. So the K6 type 1 diamonds were the production from March 2012 through to October 2012. And you can see some of the layout over here. And it was only in October 2012 when we were mining the wedge and we had to increase the pit and we crossed over the contact into the LQ that there came a change.
Yes, but unfortunately, the change came with good news and bad news. We started recovering our first type 2 white diamonds, but not necessarily in one piece. So obviously we had to rethink about what we were going to be, what we are doing or were doing in the pit, in the plant at the time. As you can see, we've got about 4 plus 100 carat stones here, and they were quite easily put back together again, and very obviously type 2s. You can, if you know what your type 2 diamond looks like, you can see the resorption and the classical sort of oily coat on the stone, and also that irregular shape. So something had to be done about the plant, but still we were obviously still recovering, sorry, not obviously, but we're recovering our type 2 browns as well. And this is a classic TLB, type 2 brown, top light brown TLB. And you can see the resorption of the stone, the irregular shape, but you can also see the hexagonal pits from the original shape from the stone. These type 2 browns, they did command some good values as well. I can say that we do get well over $2,000 a carat for these stones. Then John, you want to carry on here?
Okay, so basically what happened when we crossed the contact and carried on mining through 2013, the pit was expanding, and we didn't have much information apart from the early work that Keith Whitelock's team had done in the early 70s on sampling cow. They used 20-meter deep shafts, 6-meter diameters, and they processed it through a plant on site there. But very little was known about the rest of the cow pipe beyond the K6 wedge, which is down in the foreground here. So in October 2013, we were given the opportunity to change the mine plan. In fact, we were actually told by the CEO at the time, Mitchell Bundell, see what we can do to sort this out. So Pierre Fourie was running the mine plan at the time, still does. We went back to the history that Debbie and I were fortunate enough to have visited Cow in 2008, and we selected an area on the southern side of the pipe over here, close to the FKGK boundary and the basalt. And we were given a gap in the production, which was mostly K6 and LQ, to process through the plant at the time and see what we could get out of that part of the plant.
Okay. So then in December 2013, the pink storm arrived. And this was basically our calling card into the pink market. It was a beautiful 36 carat pink stone. We named it the Pink Storm, and it was recovered from the FK along with 50 or so smaller pinks at the same time. So now we were wondering, now, is this just a flash in the pan, or have we got a future here? And obviously it's not a flash in the pan. It is actually, we have got a very good future. And to date, we have recovered consistently from 2013 all the way through to our sale but last in 2022. And the pinks, and only in the plus 10.8 stones so far, we've recovered 108 of those stones. Sorry, John, did you say?
Plus 4.8.
Yeah, plus 4.8 carat stones. Okay, and that's all that is we're looking at on this graph here. And you can see the sort of semi-irregular recovery in the years. 2015, there was obviously some challenges in our plant and other process plant as well as the recovery plant. And then COVID hit us in 2020. We've only just started in 2022, so we don't have that many to boast about just now, but they're still coming in. So the pinks definitely do have a future. And if you look at our little box at the top of the slide here, we're now being able to identify our different facies and you know, what each one is bringing. So the K6 is the high value type 1 stones. So far to date, we've not recovered any type 2s from K6. And LQ is famous for its plus 100 carat stones, the whites and the brown diamonds, but still no pinks. Whereas the FK is bringing in fancy colored stones, obviously the type 2 pinks, type 2 whites, browns, and type 1 yellows. The GK, fancy stones, fancy colored stones, as well as type 2 pinks and purples and yellows, but no obvious type 2 whites in the GK. And here is some pretty pictures for you to look at. Okay, we've got some examples of some stunning pinks that we've recovered so far. Not all of them have been named. I think we've missed a couple of opportunities to be able to name some of our more expensive and very high quality stones. But we've got the pink Palisa, which is last year that came from GK. Absolutely gorgeous stone. The one little thing with the pink Palisa is it had a deeper color on one corner than the other, but we believe that the person who bought it and polished it has managed to pull in that extra color and make it a very stunning stone. We don't have the results of that stone. The Rose of Cow, which you saw earlier at the beginning on our first slide, 2018, and we even go down to in our plus 11 sieve size, which most of you in the diamond industry will know what that means, is the stunning pinks that we get in the smaller stones. And then we get the lighter color pinks as well, but pinks are in demand. And when they come up at these sort of sizes, 18 carats, 18 and a half carats, it's basically a fight to the finish to get hold of these stones. So the dollar per carat is nothing, you cannot put any sort of obvious number on pink stones. It's what the demand is at the moment. But unfortunately, we're still getting the odd problem here when we've reconstructed, John and I reconstructed this stone, after putting it on some graph paper, obviously it was a lot larger than what we thought. So we have been able to say that we are recovering plus 100 carat pinks. And then this year so far, in our first quarter of 2022, here's some examples of our recovered stones so far that have gone as single purchases on our tender process. We sell our stones in a tender. We don't do an auction. From 2 carats down to 21 carats so far this year. And they're very high quality, very good stones. So we have a continual set of buyers coming to our tenders in Antwerp, which is organized and controlled and conducted by Bonus. You'll see that their logo is on the top left-hand corner of these pictures here. It's a very reputable company in Antwerp, dealing with some very high profile producers of diamonds in the world. And then, but you know, so now the Eternity. We've spoken about the Eternity before. It's been reported in the Business Digest on the Lesotho newspaper in May. This so far is the largest pink official whole stone, the Eternity, 47.81 carats from FK. The Eternity is a type 2 blocky irregular, which is typical again of your type 2 stone. It's a fancy pink, it is intense, the color is evenly distributed. Bubblegum, either candy floss or bubblegum are the two colors that are often used when describing a color of a pink. And it had a very, very slight fluorescence, so there might be a hint of purple. Now, from our experience, all our purple stones that we have recovered so far are type 1s, but we'll get to those in a minute. Okay, John.
Okay, so how confident are we, you know, from where our stones come from in the pit itself? Well, from 2014 onwards, we've been keeping very good. We keep daily records, obviously, of what goes into the plant. And this is linked back to an alphanumeric block system over the pit. And every day, the 5 characters, that's the plus 4.8 characters and above, they are logged and recorded individually. They're not just weighed for their carat mass, but also we measure the ABC axes and any breakage and describe the colors. So we have a good record of where our 5 characters and above come from. And this has enabled us to really work out where the pinks have in particular have come from in the cow pit. So we know where our pinks come from, but what about the purples? That's the next step. I'll hand over to Debbie on that.
So yes, and what about the purples? All type 1 stones with a distinct color difference from the type 2. So the purples, as I said earlier, are type 1 stones. We are recovering. We have had a few purples, but quite small so far. And I think on this group of pictures, or this group of stones here in this picture here, you can see that purple right in the middle, the purple princess. But in 2008, as John has mentioned, we went to Cal to have a look at what it was just a local visit to go and see what their product was. And during that visit, we looked at their stones that they had available. And in that group of stones, there was this beautiful 1.48 purple stone, which came from, and they told us that it came from the GK, thank you, John. GK. And as you can see, it is a real genuine purple stone. So we hadn't had a big recovery of purples up to 2020, 2021, 2022. So what's going on? Do they really exist? So let's see if there was anything else to come about in our pit. And yes, as you can see from the GK, we are recovering purples, but not necessarily of very high quality, but definitely very interesting colors. This funny looking stone down here is actually a very interesting sample. It would have been example rather. It would have been good to have kept that one and studied it further. It was quite an aggregate on the inside of a purple crunched up diamond. It's more like a bullace than a purple stone, but the colors are and can be amazing. But we also get the very light color stones too. But look at the size of this thing, hey? I mean, we've got potential of getting a high caratage purple diamond from the GK. So, the contribution. Let's get down to what we're here for. Basically, we're here for the money. Okay, so what is our bottom line? So we've around about 1.6 million carats sold from December 2013 up to May 2022. And what is the contribution of the pinks and the purples? And as John told us earlier on, we are keeping records of every day's production, what's in that production, right down to the -7s, which is the very fine diamonds. And in our special range, our 10.8 plus 10.8 carat stones, of the pinks and purples so far, only 0.05% of the total production has been is the caratage, but 15.55% is the dollar. And so you can see from here that our caratage overall is very low, with 0.14% grand total of carats and 20.51% of our total dollar to date. And this graph here just gives you a very good visual of the distribution of our pinks and purples. This is done in the grainer size classes from -7 all the way to the plus 10.8s. And you can quite clearly see that our 10.8 size range stones, 0.05% is carats, but 15.55% is the dollar. And overall, our grand total over in this far left-hand corner here, only 0.14% is carats and 20% is the dollar. So let's hang on to those pinks. Let's keep going into GK. And we keep a record, which is a good idea, of all our +$1 million stones. And of that, 56% has been pink, 36% white, 2% type 2 Bs, browns, and then 4% normal type 1 white, and 2% is yellow. We've had only pink stones so far, which have we've got over $1 million for each for one of those pinks, but we've never had a purple +$1 million carat stone purple yet, but it will come. John just wants to say something.
Yeah, so basically, if we have a look at the kimberlite split out from below the colors there, there are commercial kimberlites or economic kimberlites on the down the column there in the emplacement order. Again, K6 followed by LQ, FK, and then finally GK pulse. And if we have a look, you could see quite clearly that the bulk of the stones, 80% of the top +$1 million stones, have come from the GK FK combination, and that's quite important for us in terms of life of mine, which we'll get to shortly. So let's have a quick look at the two main carriers, the FK first, and then followed by the GK. Okay, so FK is the principal source of the pinks. I think there's no doubt, although we have, to be honest, we have mined more tons out of FK, so you might say, well, that's a bit of a biased view, but nonetheless, it certainly is the main source of our pink stones at Cow. And it's mainly a volcanoclastic kimberlite in many phases of eruption. We can see that in there with column collapse around the edges, plastered on, as Johann Stiefenhofer would say, plastered on like pancakes. And they're minor basalt breccias. These are talus slope, gravity and a little bit of water wash back into the pit. And there are a number of fumaroles as well. And I mentioned the basalt breccias and fumaroles because both these elements concentrate the bigger stones as well. They tend to winnow and concentrate the crustal xenoliths as well as the mantle xenoliths and the kimberlite indicator minerals, including the diamond. So that's the FK, and then GK is our principal source of the purples. It's much smaller. It sits within the FK body itself, or it's intruded in through the body. We've got some very nice intrusive contacts that we've been able to map out, and there's a very nice magma class down there in the bottom right-hand corner. And again, it's a volcanoclastic kimberlite, but with abundant mantle xenoliths. This GK is stuffed full of mantle noddies, peridotite, and garnet megacrysts. So for Andy Moore, it's quite an interesting combination that we have here. And it certainly is the carrier of the type 1 purples, as well as it has its own contribution to the pinks as well, including the pink palesa that Debbie mentioned earlier. That was our top stone last year, actually came out of GK. Thanks. Right, so in the last couple of years, we've moved to the northern side of the pit in the mine plan sequence, and there were very little records actually from the northern side, and consequently it's always with a bit of trepidation that one runs on geology only, and you need to see what's going to come out of that geology. And it's been good news in the last, as you've seen, Debbie showed 1Q, the diamonds that have come out this calendar year, 2022, as well as towards the end of 2021 when we've been mining here. And the pinks have come totally from this northern side. So we've got a good record from the southern side of the pit. Southeastern corner was where we thought the concentration was, out of the FK GK corner down there. But in the last while, the FK in the northern side has produced. So that's really good news for us. It means that there isn't just a total nugget effect in the pipe. We are seeing a much better distribution, particularly of the pinks. As I say, the GK, the purple's not. They're pretty much confined to GK itself. So So in terms of the life of mine then, which is more than 5 years, then FK and GK, they represent 90% of the resource. So from where we had that initial type 1 stones coming out of K6, here's the K6 wedge in the corner. You can see we've expanded the pit considerably. 38 odd million tons have all come out now. And 90% of the remaining life of mine is in GK. And of course, 80% of the pinks and high quality stones, the type 2 whites as well, have come from these two units, the last 2 phases of eruption at Cal.
So we're going to continue to supply the market with our pink gems and purple hearts, and we've been lucky to have seen the results of a couple of our stones. Our buyers don't generally like to share what happens with their diamonds, but of that you can see we've done pretty well. We've got the Scarcelli, what was it, the 15 carat, sorry, cut stone came from that 32 from GK. Our purple princess came from a 3.1 carat from GK, and this beautiful pink stone here, which we don't have a name for, which was 2952. Those were the results of those, and we're hoping to get a lot more of them, but it is quite hard to get that information out of our buyers. I think it's just a little bit, the people that they buy for would like to keep that in their safes. Okay, so I hope you've enjoyed our talk, and we've just got a couple of acknowledgements that we'd like to share with everybody, and that's obviously with our shareholders and the government of Lesotho. Shareholders obviously for helping us financially, and the government of Lesotho to give us the license to mine the pipe. And Robert Cowley, thank you very much for allowing us to take part in this summer school, and also for working there. I mean, we've been very privileged to be part of this whole history making. Ray, as you know, is a legendary diamond guy, and he helps with our valuations and our identifications and anything else that we need from there. Pierre Ferry, our mine planner, and the strategist, and Dr. Paddy Lawless. Those in the industry know Dr. Paddy Lawless. He's quite a boffin when it comes to the numbers and understanding our size frequency distributions and where we are losing or gaining certain productions, and of course Bonus. Bonus, who are our marketing company in Antwerp, and particularly Jimmy. Jimmy has taken those stunning pictures with that you've seen earlier on. Most of those pictures that have got the Bonus emblem on, Jimmy have taken. So our legacy of the Pink Storm will continue, and watch this space. Thank you.
Thanks, John and Debbie. That was excellent. And we can move on to a question and answer session now. Fantastic. Okay, there is a question from Andrea King just asking about the purple color. So did you want to comment on that, Debbie and John? And
well, to be honest with you, we know that the pinks are plastic deformation, and they are from the type 2 stones. The purples, I'm not sure, to be honest. We don't know. No.
Yeah, I mean the general sort of, maybe the general consensus, and maybe Andy wanted to comment, or someone else, was that they were also plastic deformation, but I guess that's a bit uncertain.
Yeah, no, it's just, where does the type 1 and the type 2 come from, with the pink, and if it makes much difference, or if it's just excessively plastic deformated.
But the purples are really interesting in that they have their range of color, whereas our pinks are sort of light pink to intense pink. You don't have such a range of color, whereas those purples are just, you can have a light purple, you can have that really dark purple, that 28 carat stone, and then that funny red purple of the purple princess. Actually, it's just amazing the range and the purple colors.
Andy Moore, how would you fit them into your model?
Hi, John. I have not the foggiest idea, I'm afraid. I was hoping someone else would tell me.
What Well, I guess the Argyle model has always been fascinating, you know, given it produces A, cruddy diamonds, and then B, you know, a lot of the world's pinks up until when it closed at the end of 2020. And it was sort of in that marginal, I don't know, maybe marginal edge cratonic setting, and, you know, everything there seemed to be about plastic deformation. Yeah.
I don't think their pink and red stones were type 2s. I speak under correction.
Yeah.
I think you're right.
Yeah.
Yeah.
No, so Andrea, to answer the question, and there's obviously some research for you to do. So maybe you've got to speak to Debbie and John about some samples along the way, and, you know, start a whole new project. That's why we have all you students and younger people on this presentation to, you know, set the tone and set the research in the future.
Thank you.
And
yeah, thank you. And there's it will be a good project for somebody to do. Is it only the FK and GK which contains diamonds?
No, sorry. Okay, all the kimberlite types, the four economic units, and including the K12, which is a sub-economic or actually uneconomic unit under current circumstance, they all contain diamonds. And our most common form of diamond in all the four economic units that we mine now, our almost 2 million carats that have come out now, the most common diamond is the type 1 light yellow. It's either an octa, dodec, or an irregular. So I think that's the common form. They did right across all the units. And it's just those special stones that have that. There seems to be that, not seems to be, from what we've recorded, there's this passage. Type 1, K6, first phase, initial phase, high grade, full of type 1 diamonds, octa, dodec, trend, no type 2s. LQ comes in, it's the lowest grade. It's got the type 1 diamonds in it, no doubt about that, but it's got that signature of type 2, type 2A white stones and brown stones. We haven't found any pinks, confirmed pinks out of the LQ. Then you move to that next phase, the next eruptive phase, and it's a potent phase because it reams out the LQ, and that's the FK phase, and that's the bulk of what remains in the pipe. And that's where we start to see the fancy colored stones coming in. The whites, the browns, and then the pinks, as well as the fancy yellows. By the time we get to the GK, we don't seem to see any whites left. There's the odd browns, but it's almost a purple pink comes out of the GK, as well as the purples themselves. And that's what we see. But all there are is bought in that's another thing, you know, we've got Fremosite, Andy. We've got Fremosite in GK and FK. LQ not so much, and we had hardly any rejections in the K6 in the first pass. That's right, they did. Yeah. So it's an interesting. There's definitely a pattern that goes there. And the other thing is the kimberlite itself. It gets smaller with the progressive time. It actually starts to choke itself. So you've got K6, hardly any K6 left, just a little skin on the rim and the wedge in the canoe in the corner. LQ comes in, there's a bit of a belt left on the eastern side. It's much bigger than what Dave Rolfe mapped out in the Lesotho kimberlite book. It's actually a band sitting on the eastern side of the pipe. But what it does do is it reduces the size of the kimberlite pipe now. So the FK occupies that smaller pipe. And by the time GK comes around, it's only 3 hectares. That occupies portion left by the inside the FK. And the final thing that we have is a hole in the middle that is just filled with basalt rubble. And in fact, there's actually a basalt conglomerate that goes down this. It's actually quite nice. You know, with the alluvial background, we've actually got a whole bunch that the pipe ends in a sedimentary phase going down into the, we don't know where yet because we're still mining, but it's a very steep, very angular. We've even got rafts of kimberlite, rotated rafts of kimberlite sitting in this basalt gravel that are as big as a lecture room. And our basalt rafts that are sitting down there are 40 meters by 50 meters by 30 meters. So it's quite a tumble fill that happens at the very end after all the volcanic activity has ceased.
And John, just before I keep on hogging this, I mean, I guess we must compliment, you know, you and the management for the very detailed geological work done on, you know, what is a complex and generally rather small ore body. you know, and the attention to detail has clearly paid big dividends in terms of, you know, the long-term performance of this ore body.
Thanks very much, John. Well, it's a team, huh? It's a
Yeah, I
really
know,
good
I'm
team
sure it
of,
is. Yeah, but
yeah,
you're the geologist, and yeah, no, well done. But you know,
thanks very much.
yeah, I mean, to me, it's a big lesson for, you know, particularly young geologists that are going to go into mining. You know, I think one of the problems we've always had in this country, we had these massive mega ore bodies, and you mined them, and actually we forgot about doing the geology. You know, and what you've shown here is exactly the opposite. Geology is critical.
Absolutely.
Okay. Other questions?
There's a few on the question on the chat side there. John, do you want to call them out?
You go ahead.
Okay, so the next one was from Katani. Which one is massive between FK and GK?
FK is the larger of the two. It's the largest remaining resource inside. But if you mean massive in terms of structure, no, they both have structure inside them. They both have units. You know, you can see the pulses and particularly the column collapse fallbacks into that. If you're talking about structure, if you're talking about size in terms of massive, then it's FK. Oh.
Hello, sorry, we lost you.
Yeah, okay, you're back.
Okay, thank you. Yeah, Farnes, yeah, that's a thought, and it's something that I think has to be looked into.
Okay, and just trying to get comment from Andrea King. Is she still on the talk about her comments? Still lots of purples coming out of Kimberley. Ray, have you got any comment about the purples coming out of Kimberley?
You're on mute, Ray.
Yeah, John, there were plenty that came out of the dumps, but they're all a quarter of a carat, 0.1 of it.
Okay, so it's lots of small stuff. So we're losing you there as well, Ray. Presumably the load shedding's kicking in.
Okay.
John, just to comment on the other purple producer in South Africa is obviously Lace Mine.
Yeah.
Lace produce really good purples as well. Very similar colors to what we see at Cal.
Okay, and then quickly from Sean and Andrea again. You said there was erosion of the pipe. Have any alluvial diamonds been traced to this pipe, considering the interesting colors?
Yes, I think probably the best record that we would be able to track back to Cal would be the 80-odd carat that came out of the alluvials, Hopetown, mined by Chris Peroulis.
But in the immediate area, I had to go and do a little bit of a valuation of some stones from the riverbanks, from the Cow River, and the quality was very low and the size was very low as well. So I should imagine everything else got washed downstream.
Yeah. Now I think in terms of alluvials, it's because of the steep nature of all the drainages coming off the Malutis, most of and low-grade pipes for that matter. All of them are low-grade except for Dikabong. There's no real proper alluvial presence in Lesotho itself, and even further down the Orange. Mike DeWitt's done some work down there in the Alluvial North area. There were about 20-odd thousand carats came out in the first decent dolerite dike across the Orange. But in terms of linking back, the only signature stone that really sticks out is that 87 carat pink. That is more than likely a cow stone.
Okay, then Andrea just commented, yes, just started working in Kimberley. And then Cameron, could an unusually high presence of hydrogen account for the purple color of the diamonds found? Do the purple diamonds found at Cow Mine have high hydrogen content? Pass.
Yeah, we haven't tried to start our trucks on them.
Yeah, we haven't. No, we haven't done any research on those stones at all.
Research.
Yeah, I think on that there is an old article, and I think Shigley is one of the, and hydrogen at some stage was, put forward as one of the reasons for these purple stones.